My name is Sarah. My counterpart Sam is in the back. Hi, Sam. Everybody look. Yay. What we're going to do today is talk about satellite imagery, satellites, Earth observation data, and running some analysis with Python. I'll start out with an overview of what makes satellite imagery special that requires us to use specific tools and Python libraries to work with it. And then I will run us through a little bit of an overview using some common Python libraries. We'll take a break, and then a little bit later in the morning, Sam is going to walk us through some Google Earth Engine analysis on satellite imagery using Python. Everything in here you don't need to have, everything we do today, you don't have to install any prerequisites. That said, there are some optional things if you felt like it, and we'll mention those as we go. Is everybody here in the Slack channel? Should have asked that the other way. Anyone here not in the Slack channel? Okay, cool. So I'll just repeat a couple things. So the first prerequisite, optional prerequisite, is a Google Earth Engine account. When Sam walks through that, he's going to just demonstrate a lot of things running code on his laptop. If you want to follow along live, go ahead and sign up for an account now. It's instant, it's free, but you'll need that account to be able to follow along. Otherwise, all of our code is going to be open source, or it is open source already on GitHub, so you can just do it later on your own time if you felt like it. What else? Apart from that, we're going to be using some Python tools that we run in a Jupyter Notebook environment. We're going to use Binder as the environment, so you don't have to actually install anything locally. If you want to run this locally, you can. Like I said, the notebooks are on GitHub, but you'll need NumPy and GDAL installed on your machine, and unfortunately, we don't have time to do that in class today. So if you don't have that already, don't worry about running it locally. Before I get started, any questions? Cool. Was anybody here last year at this class? Good. Because we're going to do a lot of the same things and you'd be bored if you were here last year. All right. Cool. So I'm going to start with a review of remote sensing satellite imagery data. Just to keep asking you questions because it helps me wake up. How many of you work with satellite imagery as part of your normal day job or research? Okay, a lot of you do. Okay, great. So like 20, 30%. That's great. For those of you that do not, I'm going to just review some basic concepts of satellite imagery and what makes it special. Hang on, my computer's too dim to see. Yes, much better. All right, so satellite imagery. The type of data captured by satellites that we're going to talk about today is spatial. Spatial data is special in a certain way. Satellites capture imagery data, but it's not just imagery data like, cat GIFs if you go download memes and stuff. It's imagery data plus a little bit extra. And in order to take advantage of that little bit extra, that's why we need to dig into what that extra part is and use some special Python tools. So there's a couple qualities to keep in mind when you're working with this satellite data. And number one is satellite imagery can be multispectral. Does anybody know what that means? Cool. Can you tell us what that means?
A lot of the imagers, they have bands, and so they'll observe the Earth in different wavelengths, basically.
Yes.
So as opposed to our eyes, which just see the red, green, blue, they'll see like a whole bunch of wavelengths.
Exactly. Yes, so satellites can capture more than just the visual spectrum of what you see with your eyeballs. And it can capture multiple wavelengths, as she said, and it collects all of this information together in a single Earth observation data set in what we call bands. And you can think of a band in satellite imagery a bit like a layer, but it's not exactly a layer. But the idea is that you've got multiple bands in the same image collecting information about the same area on the surface of the Earth, but collecting different information. So you've got multiple values for the same pixel location. I'll talk a little bit more about that in a minute. Satellite imagery in general, especially the type we're going to work with today, is spatially referenced. It means the imagery has spatial information in it that tells you where on Earth geographically that imagery was captured or depicts. And then to go along with that, satellite imagery has spatially relevant metadata. So it has information, metadata information, embedded in or alongside the image itself that tells you its spatial reference system, its coordinate reference system, the geographic information of that imagery itself. So that's what makes spatial data special. So a little bit about rasters and pixels, because I keep talking about rasters and pixels and Earth observation data. When we're talking about the remote sensing data that we're going to be working with in class today, it's important to remember that raster data, even though I keep telling you it's special, it's just imagery data, and it's made up of a grid of pixels. So you can see on the right a zoomed in bit of satellite imagery. You can see sort of the pixelation as I zoomed in. Think of it as each pixel is like the grid on the left representing a discrete value. So pixels of the same color, for example, would have the same red, green, and blue values, if that makes sense. Pixels of different colors have different values. Depending on the resolution of the satellite imagery, each pixel covers a certain amount of ground on the surface of the Earth. Make sense? Okay. So pixels are arranged in a grid, two-dimensional grid. Has anybody here worked with NumPy already? I figure a lot of people here. All right, so start thinking about like how you would represent a two-dimensional grid of data and how that might be relevant to NumPy arrays. And a little bit later when we start working with the data itself, you can call back to this slide. So I talk about resolution a lot when I'm talking about satellite imagery. And it's a bit of an overloaded term, unfortunately, in remote sensing. We use resolution to mean a lot of different things. Most frequently, we're probably going to talk about spatial resolution, which is how much area on the ground each pixel represents. So if you talk about, for example, 10-meter resolution data, each pixel is 10 meters on the ground. So that's going to be not very fine resolution. It's going to be pretty fuzzy if you zoom in, if one pixel is 10 entire meters. 1 meter resolution, each pixel is going to represent 1 meter on the surface of the Earth. Finer resolution, you can zoom in, get more detail. Temporal resolution is the frequency between captures of the same location on the surface of the Earth. So how frequently we're imaging the same area. So you could have a 1 month temporal resolution where you image the same location every month, 1 day, 1 year, etc. What else? Spectral resolution is the number of spectral bands, the wavelengths that we're capturing. We could have 3-band data, 4-band data, 5, 6, 8-band data. Today we're going to be working primarily with 4-band data, which I'll talk a little bit more about in a minute. And then radiometric resolution, the bit depth of each pixel value, how much information we could store in each pixel. Today, in general, I will most frequently use resolution to talk about spatial resolution, the amount of area on the surface of the Earth each pixel represents. Okay, questions so far? It is quite warm in here. All right, multispectral imagery. Like I said, we're going to work with 3 and 4-band data today. All of the satellite imagery we will work with will have at least 1 band. And this illustration just shows you a little bit of what I mean when I talk about multiband data. For example, we've got a visual satellite image of, I think this is San Francisco, excuse me, where I took the red, green, and blue data, displayed it separately, and then mashed it all together. You get that pretty visual image that represents what your eyeballs would see if you were in an airplane looking at San Francisco. But the satellite captured red, green, and blue data separately, which means if you've got a satellite data set and it's got those 3 bands of data, you're going to have 3 values for each pixel on the ground. So you'll have a red value, a blue value, and a green value. Those are separate values. You don't have an RGB value. And then you're able to take those values separately, manipulate them, and perform cool analysis, or just mash them together and make a pretty visual image. But the reason this is important to think about is if you're working with traditional raster imagery, it's not going to be multiband. Geospatial data is special in that way. So if you use something like OpenCV, it's not really going to handle this at all. So that's why we are learning about geospatial Python libraries today. If you try to like manipulate or display a 3-band image in OpenCV, it just doesn't work. I forget how it doesn't work, but it just doesn't work. Questions about satellite imagery in general before I talk about the tools we're going to use today? None. Cool. I talked about GDAL. It's anybody here use GDAL? Cool. Anybody here have it installed already? Cool. About half of you. Cool. It's the foundational library. Everything that you use, like ArcGIS, QGIS, the Python libraries we're going to use today, everything is built mostly on top of GDAL. It's the basis of everything. It's amazing. You can do everything with it, but it's a little bit of a pain to install, which is why we're doing everything in notebooks on Binder today. Because last year when we ran this workshop, we tried to get everybody to use a Docker image with GDAL installed, and it didn't work so well because some people have Windows, etc. But if you have GDAL installed today and you want to run these Jupyter notebooks locally, you totally can. That's the main prerequisite. Proj 4 is another foundational library. It's actually Proj 5 now. But anyway, Proj is a foundational library that's used inside a lot of other tools, including some of the tools that we're going to use today. Now, I mentioned these just to tell you they're foundational, but we're not going to work with any of them directly today. We are going to work directly with Rasterio, NumPy, and Matplotlib. And additionally, when Sam does Google Earth Engine, he'll use Google Earth Engine's Python libraries. And a couple other things not listed here. But Rasterio is a Pythonic, more Python user-friendly wrapper around GDAL for manipulating satellite imagery specifically. And I love it. It's great. Everybody should use it. NumPy, everybody here is at least familiar with it. Same with Matplotlib. We're going to use NumPy and Matplotlib in conjunction with Rasterio to augment, manipulate, and then display the data that we're using Rasterio to read. So that's what we're going to use today. So good news, no setup, as I keep saying. At this point, go ahead and open that Doves in Space link, and it's going to take a few minutes to load. That's going to get that Binder Hub instance loaded. And I'll give it like 3-4 minutes because I don't know how long it'll take to build and load for everyone. Those of you who would like to try cloning the repo and running your local Jupyter, feel free. It's that GitHub URL at the bottom. Sorry, it's a really long URL. For those of you looking for seats, there's one empty here, and one empty there. And one there. Okay, that works too. While we're waiting for Binder to load, nobody has questions. There's a bunch of swag in the back. If you didn't get any already, make sure when we break for the next break, whenever we do that, that you grab some. Oh, okay, Sam will hand them out because he's awesome. Cool. Yeah, I don't want to have to carry those home, so please do take some. Right, I should. I should have had some launch videos here for like the waiting music. Maybe I'll put some on for the next break. Yes? I have heard this, and you're probably right. I haven't used it. But if it's there, it would have to be some sort of extension on top of OpenCV. Like, can't just be like OpenCV native. Yeah, but I think you're right, and it would make sense that somebody's done that already. I should look into that. Yeah. Question? Yes. I don't believe these are published yet, but I'll definitely make them available. I'll have to like publish the PDF, and I'll post them in the Slack and then tweet them on the hashtag, because that's what the kids do. All right. If you are still waiting on Binder to load, or you're setting up the notebooks locally, let me know. Still waiting, still waiting, still waiting. Cool. I'll give it a few more minutes. So what I'm going to do is walk through. I'm not going to do much live coding. I've already got the notebooks written, but I'm going to walk through a bunch of basic how to use Rasterio to manipulate satellite imagery stuff, and that's what we're going to do for the next, half hour, 45 minutes. If you have questions at any time, if I go too fast, too slow, please yell at me, because it gets pretty dull walking through code demos, and I might not, notice if people are looking lost. Actually, I should go ahead and get these open myself. Whoop. Come back. So I'm going to switch this. Okay, cool. We're starting notebooks, we're doing analysis. Is anybody still waiting? Still waiting for something to load? If you don't raise your hand, I'm going to assume you're good. All right, cool. All right, let me get my own Jupyter up here. So when you've loaded Binder or you've got this running locally, whichever you've decided to do, actually just so I know going forward, anybody running this locally or is you are? Hey, sweet. All right, cool. That's actually good. There are a couple things that those of us using Binder will run out of memory for later on, but I'm still going to demonstrate how to do it. Those of you running it locally will actually get a result, which is kind of cool. So once you've got it, your Jupyter server open, whether you're in Binder or you're in your local Jupyter instance, navigate to that notebooks directory if you're not already in it. And we're going to start with step 0. You can see they're nice and numbered, which is great. So we're going to start with step 0, download data. So this is where I get to take my 5 minutes and tell you about the company I work for, which paid me to be here. My company is Planet Labs. Anybody heard of them? Cool. We build and launch teeny tiny satellites, and we collect Earth observation data of the entire globe every 24 hours. So every single place on Earth is imaged every 24 hours. That said, sometimes it's cloudy in a location, so we don't have data for them. But anyway, the data set that we create is the biggest Earth observation data set ever made. And the satellite constellation that we manage has about 150 satellites in it right now. Biggest satellite constellation ever made. Pretty cool. It's exciting for a geospatial Earth observation data nerd to work there. You can get planet imagery, especially those of you who may not have worked with it before and want to set up an account for the first time. This year, though, I'm not walking you through that process because it takes a few minutes. What I'm doing instead is I've provided, Sam and I have put a couple demo data sets available, and we're going to run these download curl commands directly in your notebook to download it into your Binder instance so you don't have to, sign up for an API key. So go ahead and run these cells. And those of you running it locally, it's fine. Just do that anyway. Oh, I already have the data. That's fine. But yours will download because you don't have the data already. And these, let me see. I don't even remember what these are. Data set wise, let's see. Looks like they're one of them's from 2016 and one is from 2019. That's fine. I don't even remember where they are on the surface of the planet, but they're pretty. So we're downloading a 4-band asset, which is going to be for spectral bands. The 4-band asset is going to have red, green, blue, as well as near infrared. So we're going to work with near infrared as our different spectral band today. The 3-band is just going to be red, green, and blue. No near infrared data. We've got 2 different demo data sets here to work with, just so that we can do a couple different things with RAS stereo. Anybody having any trouble downloading this? Okay, should be running, should be fine. Thanks, Binder, for hosting all of this data for us temporarily. Appreciate you. That's what I was going to say next, yeah. Sam is our education and research liaison. He is awesome. But yeah, just to repeat it for the video and for the microphone for anybody that didn't hear, if you work for an academic institution of any kind, whether you're student, graduate student, researcher, educator, if you have a .edu email address, you can get 10,000 square kilometers of imagery for free every month for non-commercial purposes. So sign up with Sam today. Go home and download all the data tonight. Not all of it, 10,000 square kilometers. Okay, anybody still downloading? Oh, okay. Ugh. All right, we'll give it a few more minutes. Sometimes it's faster than others. Yes. So by granularity, do you mean like when you zoom in, how pretty is it? Basically. So that's what we were talking about when I talk about spatial resolution. So when you zoom in, how much area on the surface of the Earth does each pixel show? The smaller the amount of area covered by each pixel, the better it looks. If you've got one pixel representing this entire room, it's just a blur. If you've got one pixel representing my water bottle here, it's a lot better. That said, the PlanetScope data that we're working with today, both the 4-band and the 3-band, is 3-meter resolution, which means each pixel represents 3 meters on the surface of the Earth. When you want to compare that to Google, it's not a 1-1 comparison, because if you go to Google Earth or Google Maps and turn on the satellite-based map in the background, it very much depends on where you are looking on the surface of the Earth, because Google has data from a lot of different sources. So in some cases, in a lot of cases, the 3-meter resolution is going to be as good or better than what you're going to see in Google Maps. But in some cases, if you zoom in, Google's going to have finer resolution, especially if you go look at downtown Austin or San Francisco, a populated area where it's more popular and Google has gotten finer resolution data. That said, Planet also has SkySats, which is a different type of satellite. So the one I'm talking about today is the one where we have that 150 satellite constellation global coverage. And that's the 3-meter resolution. We also have other satellites that we don't have global coverage on a daily basis. We have instead on-demand coverage, so you can take a picture of where you want when you want it, but it's not globally capturing every day. And those are finer resolutions. Sam, what are the SkySat resolutions? Do you remember? 70 centimeter. Cool, cool. Thanks, Sam. Yeah.
Are all of the pixels square?
Yes. Yes.
Is that always the convention?
Yes. Sam is like, yes. I'm like, yes, that's true for us. Is there any instance where that wouldn't be true?
But I'm just curious.
Yeah, that's what I was going to say. Like, yes. In fact, we're going to do some tests in Rasterio to prove that the pixels are square. But yeah, it's definitely true for our imagery. Anybody still downloading? Cool. All right, so let's go ahead and get back out of Notebook 0. And let's start with Notebook 1. So this is going to be our first look at satellite data using Rasterio. We're just going to basically open some data, manipulate it, see what it looks like from Python. Go ahead and run that first cell. If anybody gets an error, let me know. It should work fine. I believe it's using that demo data you have. So it should load fine. Okay, cool. If it errored, we'd just have to go grab the file name from the data you downloaded. So Rasterio, like I said, is incredibly Pythonic. It's very intuitive to use. In this case, we're just going to open a data set and load the satellite data into memory. So Rasterio, let's go ahead and print it. Run the next cell. Rasterio opens data, loads it in memory, and what it does is it stores your raster data as NumPy arrays. So this is the big difficult thing to wrap your head around. If you're thinking of raster data, it might not seem completely intuitive to imagine your Python library just loading a NumPy array in memory. But remember, it's just a grid of pixels. So we've got this grid of pixel values, and that's it. So it's pretty fast. It's easy to work with. We're going to load NumPy arrays in memory. If you use Rasterio and you ask for the count of the loaded data set, it's going to tell you how many bands you have, which is 4, like we said. So if you remember, this is red, green, blue, and near infrared. So let's go ahead and parse those bands out a little bit. So something to note about Rasterio, when you're manipulating bands and looking at band counts, it's going to be a 1-based index instead of a 0-based index, which is not what you'd expect in Python. I know. Some of you are shaking your head. But the reason for that is, for example, if you are discussing satellite imagery or you have metadata documenting the imagery you have, it's going to talk about band 1, band 2, band 3, band 4. So Rasterio goes ahead and uses a 1-based index for band counts, just so you don't have to wonder, do I need to do this translation in my head? Has it already been done for me? Where am I at? So if you want to talk about band 3, Rasterio's band 3 is the same. That said, that is the most common thing that people are going to get tripped up on. I still forget sometimes, so it's just something to keep in mind. So this PlanetScope data that we're using, this demo data that we downloaded, it's 4 bands. Like I said, it's red, green, blue, and near infrared. Unfortunately, well, not unfortunately, but I keep saying red, green, blue because we're all used to saying RGB, but the band order is actually BGRN, so it's going to be blue, green, red, near infrared. So we're going to use Rasterio to read in those bands individually. You can see commented out a less efficient way of doing this where you can call the band by count number. And that's where that 1-based index could come in handy. But I'm just going to read it all in at once. That'll take a minute, but not too long. So now basically you've got 4 NumPy arrays stored as blue, green, red, near infrared. And let's take a look. Because they are NumPy arrays, you can directly use NumPy functions on them. So you can call, for example, the dtype method on one of these bands, and it's going to tell you the data type stored in that array. So in this case, it's going to be a uint16, not necessarily the case all the time. But it's really nice to be able to use Rasterio to read in your satellite data, to manipulate it, to load the bands, and then be able to augment that with NumPy functionality directly. You don't have to do anything special. Question? Oh, yeah, sorry. Let's see. Is that better? Okay. I'll try going one more. Is that better? Okay, thanks. Yeah, sorry about that. Any other questions? Yeah. Yeah, you want me to get rid of the toolbar? But I like the toolbar. Okay. Is that better? All right, cool. Any other questions? All right, cool. The very last thing we're going to do, this gets to the question, well, not quite yet, actually. We will, in a minute, get to the question you asked about square pixels. First, we're going to count how many pixels wide and how many pixels tall our image is, which is just using shape, which is going to be the NumPy method shape on the width and height. So our data is about 4,000 by 8,000 pixels in this particular data set. So this was pretty simple, pretty straightforward. We didn't do anything extraordinary, but it shows how Rasterio and NumPy can work together seamlessly to load raster data. And you don't even really need to think about the fact that it's a raster data set, an image data set. It's just a bunch of numbers, just like all of our data. Questions about this? Worked fine? Cool. This one's boring. Let's go to notebook 2. All right, go ahead and run that first cell, load our data set again. This time, just for no reason, we're going to load the 3-band data set, so it's only got red, green, and blue. Doesn't have that near infrared. Doesn't really matter yet because we're not doing anything with that with those bands in particular, but just to show that you can. So we're going to extract some of the metadata out of this data set. So I talked earlier about how metadata can store information about your data set, like its spatial resolution, its geographic coordinate system, its projection, that sort of thing. Let's see. Let's go ahead and run this. Whoops, sorry. Run the bounding box one, the bounds. So what this is going to tell you is going to be the bottom left and the top right corner in projected units. And this is how we define a bounding box for spatial data. As long as you've got that bottom left and that top right, you know the box that bounds this data set. You don't need every corner. That makes sense, right? Okay, cool. This is going to be in projected units. Our data set here is in a UTM coordinate system. So in this particular case, it's going to be meters. But anyway, that's our left, bottom, right, top corners. You can use that to do things that we will do later. But easy to get, you just do bounds. Let's get the dimensions. So on the previous notebook, we got the pixel dimensions of the width and height. Let's actually get the map dimensions. So how many meters wide, how many meters tall is our image? So we're just doing actually really simple math here with that bounding box. We're not doing anything special. We're just subtracting the left from the right and the top from the bottom, or the bottom from the top, which will give us the meters measurement of the width and height. So we've got 28,000 meters, 14,000 meters height. Not bad. Any errors, any problems? No. Okay. This is boring. Rows and columns. Let's print that. If you remember, I talked about, question? Oh, okay. I talked about, this is just a grid of pixels, so we've got rows and columns. We have a few more columns in this data set than the previous one. If you remember when we got that pixel width and pixel height, that's technically going to be the same as the rows and columns measurement. We're just getting it in a different way here. Remember, this is a different data set, so that's why we've got columns of 9,000 instead of, on the previous one, it was 8,000 something in height. Or in width. Rows is also the number of pixels wide it is. Same thing. Let's see. So go ahead and run the next cell, and then I'll tell you what's going on here. Earlier I told you this data set is going to be 3-meter resolution. So what we're doing here is we're going to take the width and divide it. We're going to take the satellite data's pixel value width and divide it by the meters value. To figure out how many meters go into each pixel. Same with the height. So that's another way of answering the question of how much area on the surface of the Earth is represented by each pixel. And so we've got a value of 3 for each, 3 width, 3 height, which means it's a square pixel, which means it represents 3 meters by 3 meters in all ways. And this is a roundabout way of answering the same question you asked earlier about are the pixels square, and about the information we said earlier about how much data on the surface of the Earth are we representing. All right, CRS, as I said, the coordinate reference system, it's going to give you back an EPSG code. Anybody familiar with EPSG codes? Okay, about half of you. I'm going to open something real quick. It's a really useful website, spatialreference.org. If you have not worked with coordinate reference systems very much, you might not be familiar with this EPSG code representation. And if so, you can use this website to look up those codes. So go back to our notebook too. We got EPSG 32610. What you can do is copy that here. You could search it, and it will return what your coordinate reference system is. In this case, it's UTM 10 North. And you could get that coordinate reference system in multiple different formats, including like well-known text or JSON, or, depending on the data set working with, you can get anything. But it's really nice to use this website to just look up a code if you're not familiar with it, because I certainly don't know most of the codes that pop up. And it's a nice reference if you're not sure if the data set is, the right, or it's in the right projection or coordinate reference system. Cool. So like I said, this particular data set is in a UTM projection, and it happens to be 10 North. Which, if you're familiar with projections, you'll know that means, like we've demonstrated, that the map units on the ground are going to be in meters, because meters is the projection unit. So let's do something a little bit more interesting here. We're going to take pixel coordinates, so the actual pixel grid column coordinate, and convert that to world coordinates, because we can use functionality built into Rasterio that's going to transform between the two. Since Rasterio already knows what the coordinates reference system is, it can automatically transform a pixel coordinate using that CRS into a world coordinate. So first we're going to take an upper left pixel and a lower right pixel. Just to be confusing, rows and columns are 0 indexing versus bands. Nothing except bands is 1 index. So everything is 0 indexed except for bands. Bands are 1 indexed. But rows and columns are 0 indexed, so if you're used to working with NumPy arrays, then it's going to function in the same way. So we're going to take the width and height and subtract 1 so that we get a 0 indexed lower right corner. And we're going to use this dot transform method that comes in Rasterio. What that's going to do is it applies what's called an affine transformation. Actually, I don't know if it's affine or affine. I've heard it both ways. Anyway, it applies the transformation, which is basically doing matrix math on this grid of numbers, and transforms them from those pixel coordinates to the coordinate reference system coordinates. Does it for you, which is great. So that top left, which is 0, 0, is going to be this long 62 blah, blah, blah. That's the meter coordinate, the UTM zone north, zone 10 north coordinates for that top left corner, and same for the bottom right. Does this make sense? Is it confusing? Does everybody have an idea of what happened? Yeah. That's a good question. They are not. Because what we did at the beginning is we asked for the bounding box, which gives you the map coordinates, the coordinate reference system coordinates already. You're right. They are the same coordinates, or they should be. But what we've done is generate them sort of manually instead of calling for the bounding box. We've taken what we know is 0, 0, which is always going to be our origin, our top left, and then our width and height in pixels to get our maximum bottom right in pixels, and then transform them. But you're right, they are the same coordinates we got with the bounding box. Other question? Cool. So that's just demonstrating, that's actually a good question. It's demonstrating multiple ways of manipulating the data to get the same information. Like say you didn't know that Rasterio had a bounds method, but you wanted to calculate the bounds, you can just brute force it by applying a transform to the pixel numbers. And then all of this information that we've been talking about, or a lot of the information and then some, is contained in the image's profile. This is basically a dict of all of the metadata for this particular image. So to dissect this a little bit, we can see that this image is a geotiff. The particular D-type on this image is UINT 8, not UINT 16. The previous image, the 4-band image, was a UINT 16. No data values is none. That means if a pixel has no data, how are we representing it? Some data sets, it might put a 0 here, but 0 is technically still a value. So this is representing no data as none, so it's going to be a Python none value. Tells us the width and height in pixels. The count is 4. That should be the band count. I don't remember what 4 means here. It is still a 3-band raster. Let me double check that on the break and get back to you, because I think that should be 3. CRS, like we said, is this EPSG code. Here's the transform directly, which is, like I said, it's a matrix you can apply to any pixel value, but you can just call it, you don't need to know what that is necessarily. You can just reference it when you need it. Block size, X and Y, is going to be 256. It is tiled, which we're not really going to get into today, but tile data means, in this instance, you could reference a tile, a specific section of the image, which helps if you've got very large data and you don't want to load it all into memory at once. You can load a tile. Compression is something we're about to look at, so for now just note that it is LCW compression. And then interleave is pixel, which I don't even remember what it is. So that's fine. But file compression. So rasters use compression to reduce file size. There's a lot of different compression methods. Some are lossy, some are lossless. Everybody familiar with the idea of lossy versus lossless? Most of your heads are nodding. Lossy basically means we're going to compress it by removing some values that are unimportant. Lossless means we compress it, but we still retain the original values in each pixel. Lossy, not so great for analytic purposes, but it's great for reducing file size for data transfer. All of the planet data that you can download, including the demo data you have today, is in a lossless compression, which is that LZW. But let's, for the hell of it, make a lossy compressed version of the same file and compare it. So what we're going to do, this humanized library is completely arbitrary. You don't need it. This is just so you can get a nice representation of the file size. So let's look at the file size of that 3-band image. It's about 69 meg. So this more or less is going to show us how to write a copy of a data set with rastereo by and change some of its metadata to apply a different compression. So we're going to save profile, which we technically did a few minutes ago anyway. Whoops. First you have to load the data. So we're going to save profile, which we did a minute ago, and then we're going to change the compressed value in there, which is currently LZW, as we saw a few seconds ago, to JPEG, which is going to be lossy. And then we're going to write out a new copy called compress.tiff. This is just going to put it in your data directory if you're in Binder or wherever you're running this locally if you're not. And then you can check the file size of that JPEG compressed version. Same file, minus a couple of pixel values. It's a lot smaller. But that's just a good demonstration of how easy it is to read in and write data with rastereo. And that profile, which is just a dict, you can modify values in it to directly affect the output that you're writing. All right, questions on this? Yeah. Yeah. Oh. Yes, thank you, because it's an old data set. I was like, what? Thanks. I shouldn't use 2016 data in this demo, because it confuses me. Yes?
What is the convention for the lower left corner that we had earlier?
Mm-hmm.
Is that it was a 3 meter by 3 meter pixel. Is that the center coordinates of the pixel, or is that the lower left? Conventions have become very confusing.
That's a good question. The entire pixel is going to be that coordinate. We don't have any finer grained coordinate for our image. Like, the pixel is the smallest unit we can measure. So it doesn't really matter if it's the center or the bottom left. We're defining the entire pixel. Oh, I misunderstood the question. Sorry. Oh, is that what you're asking, the 3 meters?
No, what I was asking, I think it's the question.
Okay. Gotcha.
If you wanted to assign a value, a coordinate to the pixel, where would you assign it, I guess?
I feel like this is a philosophical question because the pixel is the smallest unit. I suppose we could consider it center, but there might be a different answer there, actually. But yeah.
Okay, thank you.
Other questions? All right. Let's keep doing these. They seem a bit boring, but I promise you when we start doing like actual use cases and real world scenarios, it's nice to have these to reference because you're like, how do I write a new file in rastereo? Oh, that's how. So we'll run through a couple more, and then we'll take a break, and then we'll come back and talk about Earth Engine. So we looked at reading in data and seeing a data set's coordinate reference system, and then we wrote out new data with different compression. Let's do a couple more things. We're going to read in data. We're going to clip it. So we're going to chop it up based on a new boundary, and then we're going to reproject it to a new coordinate reference system. So a lot of things. Let's go back to using our 4-band image, read it in. And this is going to show us, let's see, hopefully it loads in Binder and doesn't run out of memory. Oh, I'm not in Binder, so of course it'll work. If this second one doesn't work for y'all, just pretend it did, and it looks like this, because Binder occasionally runs out of memory depending on what we're doing. But basically, rastereo.plot is a shortcut, is a wrapper around matplotlib. So we're just plotting these NumPy array values directly in your notebook, and it's actually a satellite image, which is pretty cool. We didn't do anything special here, so we've got some random color ramp applied, which is funny, and we've got also, it's trying really hard to give us X and Y labels, which is kind of impossible because it's not a data set that you can have a X and Y axis labels for, but I tried. But nonetheless, this gives us just a quick way to see the general shape of our satellite image and what it might look like. I can tell already this is San Francisco again, because I use that a lot as demo data. So we've got San Francisco here, and then across the bridge we've got Oakland, but we'll see this better later. So I'm gonna take an arbitrary bounding box, a boundary that I've drawn, and I want to chop out a section of this image. We're going to call this clipping, and we're going to use a GeoJSON data set, which is a vector data set. I didn't talk about vectors yet today. We're working mostly with rasters. Vectors, if you're not familiar, represent points, lines, or polygons. In this case, we're using it to represent a polygon, and it's just a shape drawn with 4 points and lines connecting it. And we use GeoJSON file type to represent it. And we're going to take that shape and cut our satellite image to this shape. We're using Rasterio's counterpart library called Fiona. Rasterio and Fiona both are wrappers around that GDAL foundational library I talked about earlier. Fiona is what we use for working with vector data. Rasterio is what we use for working with raster data. Fiona should have a more easy to remember name to know that it works with vector data, but Rasterio is easy enough. So we're going to use Fiona just to open that GeoJSON file that has our polygon in it, and we're going to call it an AOI because we're defining an area of interest. We're interested only in this subsection of our very large satellite image. So we'll go ahead and load it in. This is just an illustration. The red is that polygon that we just loaded in, that GeoJSON file, and below it I've just got a section of our original raster data. So what we're going to use is Rasterio's mask function. So we're basically going to tell Rasterio, take this polygon, mask your raster by it, and then everything on the outside we're going to set to a none value. So we're going to get rid of it. We're going to set to no data. So that shouldn't take very long to run, but I'll give it a few seconds in case Binder starts choking. But basically, using that crop equals true argument is just setting everything outside of that polygon to be no data, which is the equivalent of cropping a raster. Rasterio is nice is also going to update your bounding box, so you don't have this massive bounding box with a lot of no data values. It's going to shrink it to fit your data values. So we have that data, we've done the crop. We haven't written it anywhere yet. It's just a NumPy array with spatial information attached to it. So let's write the data set. What we're going to do is copy the metadata. This is very similar to the profile information that we used on the previous screen. It's just formatted for metadata. So we're going to make a copy of it, and then we're going to update transform, which we actually created during the crop. That's just making another one of those affine transforms that you can apply to convert between pixels and coordinate reference systems. So we're going to update the metadata with this new transform. Then we're going to change the height and width so that we don't have a massive image full of no data values. And then we're going to write it out as a geotiff. So we're not doing anything like changing the compression. We're going to keep the same compression that was on the original image. We're not changing the CRS. We're going to keep the CRS on the same image. All we're updating is its shape, size, and transform. Go ahead and write it. Shouldn't take very long. And then you can display that directly in Binder. And you can see that it's now the shape and size of that polygon, that red overlay we showed previously. And we've just cropped our large image to it. So, yeah.
Maybe I'm missing a little bit. But
That's okay.
How did you get the polygon?
Yeah. I sort of went too quickly over that. Let me actually show you what it looks like directly. I'm going to show you the data set in GeoJSON, which isn't very helpful, but it will help me talk about it. This is the data set in GeoJSON itself. This is that polygon. So GeoJSON is just a spatially aware form of JSON. So if you've seen JSON before, it's the same thing. What we did is we read that in using a Python library that knows how to interpret JSON and read it as vector data that's spatially referenced. What's another way I can show this to you? You can see, for example, this GeoJSON has a coordinate reference system in it. This EPSG, I don't know, this is probably really hard to see. It's got the same EPSG code. This is just a data set that I created ahead of time to be able to do this. Let me actually load this yet another way. Oh, no.
Is it specific to that location on the Earth?
It is.
Okay.
It is. And I gotta remember where things are. You get to see everything on my computer, which is too many things. Live coding is so fun. Why didn't it zoom into the area? Well, I think GeoJSON IO is not working, so that's cool. Oh, you're right. Yeah, you're right. It's the wrong one. You're right. Well, it's another way of viewing the data. If I had QGIS installed right now, which I do not, which is why I didn't open it, you could open the data set there. Basically, it's a polygon that I made ahead of time that is specific, already covers the same area. It's like a subsection of San Francisco. And I just drew a random box that covers the same area so that I can crop that big image down to a smaller one.
So if we want to do this ourselves, we have to make that image ourselves, or that polygon ourselves.
If you want to replicate exactly this with the same demo data, the polygon is already there for you. If you want to do it with another image, yes. A lot of times, though, this comes in handy because maybe you already have a polygon defined somewhere else. Say you're looking at deforestation problem in South America, and you have a polygon that defines the parcel of land that you're looking at. You would just use that polygon, apply it to all the raster data to crop it to your area of interest. But you can also use geojson.io, for example, in your browser to draw a polygon and get a GeoJSON file. Or if you have desktop GIS software like QGIS or ArcGIS, that's what you would use to create it. Other questions? Okay. So yeah, this was our original data set. You can see this is long, rectangular. This red polygon is what we cropped it to, and then the result is this. So it's not long and rectangular. It's about the shape of the polygon we cropped to. The next thing we're going to do is reproject it. So right now everything is still in that UTM zone north, zone 10 north coordinate reference system, and let's reproject it actually. If you're not familiar with what that is, basically we're just going to apply a different coordinate reference system, transform it into this new coordinate reference system. In this case, we're using EPSG 4326, which I'll show you what it looks like if you search it here on that spatialreference.org site. Sorry. If you're not familiar with 4326 already, this is the most common web mapping coordinate reference system. It's going to be used in all of your spatial web applications. It's just WGS84 Web Mercator. That's not Web Mercator. Just WGS84. But anyway, let's take Rasteria Warp, apply it to our coordinate reference system, tell it we want to transform into 4326, and then apply it all. So go ahead and run that one so we set our target, and then I'm going to talk about what's going on here. I talked a little bit about transforms already because we've been using them. Basically, you never are going to write your own. You're always going to let something like Rasterio generate it for you and then apply it to your data in the way that you want. So here we're going to let Rasterio generate the transform for us. It's going to calculate it using this calculate default transform, which is going to give us that transform that we want to apply to take our data from the UTM coordinate reference system and turn it into 4326. So we're going to let Rasterio generate it, and then in the final step, we're going to write out the new data by applying that transform here, and then changing our CRS to the target CRS. So when you reproject data, the width and height is probably going to change, so that's why we're rewriting the width and height values here as well. Make sense? Okay. Boring. Yep. All right. Cool. Let's go ahead and apply it to the new file. And lastly, we'll just open it to look at it. Looks more or less the same, but the shape has changed slightly. All right, that's it for this one. We have a couple more things, but would anybody like to take a break now or just keep going for another 20 minutes or so?
I actually had a question.
Mhm.
I'm seeing that when it does the reprojection, it doesn't do anything with the pixels. It just says this pixel is now here. And
Right.
doesn't-
Exactly. It just shifts it. Yeah. So the pixels are still going to be square and they're still going to be 3 meters resolution. Did I see another hand over here? Nope. Okay. Cool. All right. Yeah. Yeah. That's true. That's true. I forget that because I'm not running it in Binder, so I don't really care. Okay, so we've done clip and reproject. I'm gonna look a little bit more at manipulating rasterio read in data with NumPy and then visualizing it and plotting it. Then we'll take a break after that. Okay, cool. This time we're working with a 3-band data again. Sorry, 4-band data again. We're gonna read in all of the bands. Cool. You remember I told you grid of pixels, just a NumPy array. And just to prove it, you can look at the type of the band itself, and it's going to tell you it's a NumPy ND array. Just in case I haven't hammered this point home enough, the number of dimensions in the NumPy array is 2 because we got rows and columns. And then this is the D type, which we have already looked at for this data set, uint16. All right. You can use min-max, NumPy min, NumPy max. You can apply it to the the array just like a regular array. It'll give you the min-max values. Everything here has a min of 0. Makes sense. We don't have any negative values. And then the maxes vary. So we've got a red, green, blue, and near-infrared max. All right. So the last thing we're going to do here is we're going to take an arbitrary pixel that's 10,000 meters, or 10 kilometers east, 10 kilometers south. So it's 10,000 meters in from the left and then down from the top. And we're going to just grab the value of the pixel at that location for each band. So this is nice. You can grab a particular location on the surface of the Earth, and then you can read all of those band values there. So you've got a red value, green, blue, near-infrared for the same pixel. I won't bore you by walking through everything that happened there. We're just doing the math to find where that pixel is, and then we're reading in each band that pixel's location. It's a good question. It's because the red value is going to have a different max than the green value, for example. How much red was visible on that location versus how much green versus how much blue. More or less in this case, yes. It's the way of representing the spectral wavelength that was read in at that location. So in this case, we're looking at red, green, blue, and near-infrared values, which are going to all vary. But it's going to be the same location for this particular pixel in this example. They just have different values for each of those bands. Questions about this one? Yes?
The band order up there was just typed in, I noticed.
Yes.
Is that the predominant convention or?
Yes, it can vary, but you can always check it with the metadata, but it depends on the source you're getting it. For the PlanetScope data in particular, it's BGRN, which is in the metadata. For different sources, it may vary, but it just depends.
Is it always labeled? Yes.
Yeah, it should have documentation or metadata with it to label it, but in some cases you may get a bad data set that does not have that. Yeah, because we have good data sets. It's blue. Yep. So GDAL info can accurately read it for ours because we have it in the metadata. Some data sets it might not. Yeah. Landsat's different. Other questions? Yes.
What units are these values in the pixels?
Good question. How would you define what the unit is for the spectral value? Okay. Other questions? All right. Let's look at visualizing some data. So we're going to use matplotlib to start plotting these images. I did that already a little bit using Rasterio Plot Show, the wrapper around matplotlib. We're going to do a little bit more customization of the plot that gets displayed just so we can actually see something semi-useful to satellite imagery. So for the sake of efficiency, I'm going to load that clipped image that we created a few notebooks previous, just because it's smaller. And then we're going to open it up. I'm putting a fake scale on here just so we don't have to talk about the scaling value that Sam was mentioning a minute ago. I'm just going to fake scale it by 10,000 for display purposes. Load in each band. So then what we're going to do is use NumPy dstack. So we're going to create stacks of the arrays here. We're going to make one RGB stack, red, green, blue, and one NRG stack, which is near infrared, red, and green. And the reason we're doing this is so when we plot it, we've got two different ways of plotting the data. Let's go ahead and run that. So we're using IMShow to load the blue band. So this is the blue band only by itself. Displayed with no red value, green value, or near infrared. This is that cropped image. You can see some clouds. You can see San Francisco. You can see water. Not really interesting. Let's load the green band, though, and change the color map, and then add a color bar to it. If you have not used matplotlib to display imagery in a notebook, for example, before, I'm going to kind of just sort of light over a bunch of things here because matplotlib, a lot of this stuff is not going to be straightforward, especially when we get into like customizing the display. The documentation is great though, so you can just hand wave at this and pretend you know what it's doing, but basically we're just displaying imagery in a notebook using Python because we can. So this is a different color map, the GIST Earth color map applied to the green band, and then we've got a bar up here, which is trying to represent our data values. And still has X and Y labels that are not very meaningful because our data is not just like a nice gradient from the bottom left to the top right. It varies. So we'll get rid of those. And we'll plot the red band with the Inferno color map, because why not? And we'll turn the axes off so that we don't have those axis labels. So this is a little bit nicer, a little bit more useful. Don't really have that distracting X and Y label. But let's display some of those stacks that we did. For whatever reason, I'm recreating the stacks here. That's fine. I was probably asleep when I did this. But let's plot the RGB. This is going to show us, you can ignore that for now. This is going to show us a more or less true color representation of the image because we've stacked the red, green, and blue. And now we're displaying it visually. So it looks a lot like what you would see looking out of an airplane window if you're flying over San Francisco, which is cool. And then let's use that near infrared red and green stack that we created a few minutes ago to display what we call a false color composite. So what this is going to do, this is a common way of representing raster data, Earth observation data. It's going to highlight vegetation. So here you can see Golden Gate Park up here in the northwest. If you've been to San Francisco, this is the Presidio. We've got the park here. Those are very grassy areas in what's an otherwise very urban city. So you can see how they're really highlighted in this near-infrared representation. Now this is the same data set we've got up here in that visual representation. But if you were just looking at the red, green, and blue, it's very hard visually to pick out, where is there more vegetation in this image than in urban areas. So by taking that near-infrared band doesn't represent anything you see with your eyeballs, but we can apply that and falsely color it, make it pop, so we can color it red in this case. And then we can see what is reflecting more of that. So we can see where the grass is in San Francisco, basically. So that's nice. You can do all of this in desktop GIS software as well. You don't have to stay in a Python notebook, but we write Python, so why not stay in a Python notebook? Like, why do you need to open ArcGIS? But yeah, you can use Matplotlib in that way on raster NumPy arrays right in with rasterio and display data. Questions? Works well? Cool. Last one I will walk you through, then we'll break. All right, I'm going to load the 4-band data again. I'm going to load each band, and we're going to plot a histogram of pixel values. We want to see what is our most common pixel value. We're going to plot, least common, most common values. So there's a lot going on here. This is a lot of Matplotlib plotting stuff. If you're familiar with it, you know what's going on. If you're not, take an hour, read the docs, figure it out, because otherwise, I don't mean that to be rude. I just mean there's no other way to just grok this magically because it makes no sense otherwise. But we're going to create a figure. We're going to add a subplot. We're going to add a title. We're going to label the x value, or the x-axis. We're going to give it a y label. This is interesting. What we're going to do is take anything that has a no data value and ignore it because we don't want to plot it. It's not useful to us. We only want to count pixels that have values. We're going to bin this into 20 bins, so we have 20 bars for an arbitrary reason. You can change that. That's fine. But I'll leave it for pretty. I'm going to make it light green. You can go here, see all of the colors that you might be able to label it. Whoops. Then we're going to actually call the histogram method on this, apply all of our things, and we're going to save it as an output PMG, and then I'm going to plot it here. Which, cheating, it's already saved in the notebook, so you don't actually have to run this. Great. Very few pixel values over 10,000. Most of our pixel values are below 5,000, so that's interesting. Excuse me, this is the blue band, by the way. You can be any band, but we're plotting the values of the blue band. This is not necessarily useful to us right now, but I'm showing you how to do this because later, when we're actually, manipulating our data to get a specific index or analysis result, it might be important to us to see where are most of the values because it represents something actually useful. So this is just showing you how to make a histogram of the pixel values. For the blue band, we don't really care, but now you know how to do it. All right, zoomed through that. Any questions?
Do you often see power laws like that in satellite data?
See what?
See power law distributions like that?
Sam.
Yeah. I didn't get the question.
That's the Sam question.
Do you often see power law distributions like that in satellite data?
Yeah, I don't know.
It depends on where the picture is taken, I guess. If the picture has a lot of ripe soil or urban areas, then the pixel value will be really high respectively. Also, if it's too cloudy, then you will see the same distribution that there's a lot of bright pixels that are super high. If you have a lot of water at one edge, then what you'll see is really low pixel value. And it also depends on the band that you're visualizing for this picture. So, it depends on that. Also, before we go any further, one correction, radians does have a unit. It's watts per steradian per meter squared. I got confused. Reflectance doesn't have a unit. Because reflectance is a ratio and radians is just how much you measure.
Cool. Other questions? All right. We're going to take a break. And what we're going to do when we come back is, well, Sam will talk about Earth Engine. There are more notebooks in here that I will not walk you through in a boring style. But what they are is set up that you can, actually, I'll show you now. They're set up that you can work these either in class or later, and they're going to be hands-on exercises. Each folder is going to be a separate exercise. Actually, since you're talking about radiance and reflectance, let's talk about that. There's going to be 2 notebooks in each. One is a key. It has the answers already filled in. All of the code is complete. You're going to want to open the non-key one if you want to do it as an exercise. And just to demonstrate, yeah, I know. Ignore that for now. It's going to have a lot of information about the actual use case. In this case, it's talking about converting from radiance to reflectance, that ratio that Sam was just talking about. It's going to explain what that means and then where to get the data in the metadata that comes along with the data set. And it's going to explain how to calculate it, and you're going to try to fill in the Python yourself to do it. If you can't, it's in the key. So we've got 3 of those exercises, which will apply all of that boring stuff I just walked through with rest area and NumPy to actual scenarios. But first we're going to talk about Earth Engine. Depending on how much time we have later, we might do some of these in class. Cool? All right, let's take a break for about 15 minutes and get swag from Sam.
So while I give people and gonna get things started, what I want you to do is there's a folder on the main binder page which says GEE, that's Google Earth Engine. Go there, open the setup, and there's a few things that you should learn or run basically, and just click on run on all cells or just run them one by one. It takes a little bit of time. That's the reason I'm making you do this. The last bit, which is the authenticate Earth Engine, is what we will get up. How many of you don't have a Google Earth Engine account? It's okay. Do you want to get one? Okay. So there's a sign up link right here that I pasted some time ago, which was signup.earthengine.google.com. It should be on the Slack channel. So go here, and it's instantaneous. It'll just say log in with your Google account, and you'll fill in some profile information. You'll just say, here's what I'm thinking about doing with satellite data. And even though the email will say, look forward to an email welcoming you to Earth Engine, you should have that account. Yes, go ahead. You have a question?
Oh, that's about it. My problem. I've been waiting for this.
Don't worry about it. That pretty much means that you should have an account. If you have an account, you can test it out. There's a website called code.earthengine.google.com, and I'll post this on the Slack page. If you see something similar to what you're seeing here, that means you have an account. If you get an error or says pending or in any way, then we have an issue, and we'll try to resolve it. But I'm pasting it for everyone's reference here. Yes. It's also on the Slack channel. Someone pasted it right here. Yeah, doves.in space. Yeah. Ah. Okay. There you go. So check for those 2 things, and then go through the setup IPython notebook. Okay. Give it a few seconds. It's not like. Oh, you did? Okay. Glad you're interested. Huh. Interesting. How many of you are getting glad you're interested? Keep exploring or something similar. Okay. Yeah, Google might be like wondering why there's so many requests coming in suddenly. Worst case scenario, don't worry about it. Enjoy the presentation. If you're not able to log in, or for some reason if the account is not accepted by Google within like 5-10 minutes, there used to be an actual person approving these requests. It's no longer the case, which is good. So yeah, if that's the case, don't worry about it. I'm going to show you the demo, and these IPython notebooks will be available, and you'll be able to replicate everything once you have access.
What was the notebook that you need to open and start?
Yes. So if you go into the GEE folder, it's setup. It's just called setup. And run the first one and the second one. And second one usually takes a long time. That's the reason I'm making you run this right now, because it's setting up leaflets and extensions and other stuff. The authentication of Earth Engine will only work if you have an Earth Engine account. It will not, unfortunately, if you don't have an Earth Engine account. But like I said, it's going to be an easy tutorial. And the idea here is to give you a flavor of what analysis of hundreds of gigabytes or terabytes or petabytes of data looks like on a cloud compute infrastructure. That's the idea. Because as data sets get finer and finer resolution, we're talking about 3-meter data sets, the sizes of these data sets are increasing. How many of you use drone data or have used drone data or played with it in the past? What's the size of those images? Huge, right? And usually, if you get into the domain of like centimeters, so you can get like 2 centimeter, 3 centimeter drone data, you're talking about terabytes that don't fit in your backpack anymore. So you have to keep them somewhere, and you have to figure out a way in how you can analyze them, chip them, and do all of those things. And I don't think you can load them into memory. You can try, but a lot of these things will not load into memory unless you tile them up or you grid them. So that's the reason that a lot of these cloud-native infrastructures are becoming more and more relevant. This is in no way the only available way of doing cloud-native analysis of satellite images. There are some other platforms. There is Radiant Earth used to have a platform, but they actually got out of it recently, which was also free, unfortunately. DG, Digital Globe, used to have one called PyGBDX. They also closed down their community edition. So for now, this is the only community edition version that I know of. But if you, and also there is Pangeo, of course, that allows you to do some analysis on the cloud using cog tiles. But talk to the Pangeo folks. I don't know much about Pangeo. So, okay. Let me give you, sorry, go ahead, question.
So in the previous thing, there was a lot of geochip. It looked like geochip data, basically, right? The
Yes,
files.
yes, absolutely.
Were those cloud-optimized geochip or just regular geochip?
So since, I think, 2018 or 2019, we have been producing cloud-optimized geotips.
Oh, cool.
And you have the capability of actually tiling them up. We have a tiling service as a part of our API service. Like, you can tile them and send them somewhere at different levels, and then you can go and access them as you need it. So,
Nice.
yeah.
Cool.
Okay, so just to give you a little bit of flavor about Google Earth Engine, how many of you actually know what Google Earth Engine is or have played with it in the past? One person. That is so awesome. Actually, that's great. So to give you an idea of what Google's vision was, and I'm going to like basically steal their thunder, and I'm going to do my version of what Google's vision was. So I don't represent Google in any way, just so you know. So yeah, in 2013 or 2014, there was an interesting paper that came out from University of Maryland, which was this one. If you look at Hansen forest cover, and they produced this image, and along with this scientific paper, this was one of those very few scientific papers that came with an app link directly with it. Now, what it allows you to do is it allows you to zoom into any location and look at forest loss and forest gain. So you can look at forest loss as it has occurred in different parts of the world, forest gain. And this was the first application where they has used all of Landsat data set across all sensors for the last 30-something years. This is petabytes of data. To visualize or to even analyze this data sets would have cost a lot of money. Thanks for making Landsat free, whoever made that decision, by the way. But we did the math, and it would have cost $330 million of NSF money just to do that analysis, just to ask for that. And this is just the data cost. I'm not talking about the analysis cost at all. That would have cost more money. Go ahead. Do you have a question? Oh, I'm sorry. Totally roaming around with the mic. Can we open this?
You have to use both of them too.
Can you actually unhook them?
You have to use both though.
Why?
One for the room, one for the camera.
Oh, I see. Okay, never mind. I will stand here. No theatrics for you guys. Okay, so this was one of the first papers that came out. This was kind of shocking because an analysis at this scale, of this resolution, had not been done. This is 30-meter imagery of every pixel that has undergone a loss, and it's constantly updated. That algorithm actually exists somewhere, and it's updated as newer and newer Landsat imagery gets available. This also opened the door and gave a very good pitch for a lot of people who were interested in how this analysis was done. And Google Earth Engine kind of came into limelight because, and I wouldn't give the entire credit to this paper, but this paper was relatively important in making this kind of famous. And like, look at it, and I was like, oh, the appeal is really great. You can do an analysis like this. Fast forward a few years, and you have Google Earth Engine, which is kind of like Google Earth, but different because it's a two-dimensional representation of the entire Earth, first of all. And second of all, you can actually analyze the data sets. You don't just visualize it. You don't just open up and zoom into an image, but you can actually render an image. You can go into a catalog and search for images. At this point, they have about 430 something images, and I actually maintain a running list of how many images they have. So I'm going to show it to you. Okay. I updated this like 9 hours ago, but this is all the images that they acquire, and that's about 490 images. And if you scroll to the right, it'll tell you what is the start date, end date, what are the tags, whether or not it's a collection or whether or not it's an image. So Earth Engine is a platform that also serves it has a two-part role. It serves as a data repository, so it saves up all of these public data sets. So it has all of Landsat, it has all of Sentinel-2, all of Sentinel-1, and it keeps on processing them as new data comes in. So it keeps on acquiring and curating these data sets as well. It has all of MODIS, and pretty much anything that you're interested in, you can go into the code editor, which is this if you're logging in. And the website is code.earthengine.google.com, right here. Okay. If you want to type in, for example, if I want to type Landsat, I can start typing Landsat 8. And if I want to type surface reflectance, I said, okay, tier 1 surface reflectance data set. It's a collection. This will give you some information where the data is sourced from. And you can click on import. And what you essentially did was kind of added a link to this entire collection or bucket of imagery that you have over a given area. So I am going to go, let's go someplace completely, let's go to this part right here. What I'm showing right now is not in Python. It's going to be a little bit of JavaScript, but I'm going to switch really quickly into Python, and I'll tell you why I'm showing you the JavaScript bit first. So what I did was I zoomed into a part of the world, I drew a geometry, and what I'm going to do is restrict my image collection that I imported, which was Landsat surface reflectance, only to this geometry. So I can say filter equals to collection, filter bounds, and I'm going to bound it to my geometry. It's going to be a large data set because it's been there for a couple of years. So let's also put in certain dates so that it becomes easy to run. So I'm going to give it 2019 0101 and 2019 0601, let's say. What we want to do first is see how many images actually intersect with this geometry. I want to find only that much, okay? And now, notice that I have not loaded anything into RAM. I'm not doing anything. All of this analysis is occurring at Google's server. So that's the other beauty of it, is you can have a Raspberry Pi, and you can run the same exact analysis as you can have a computer with a GPU. It's not dependent on your platform. And I said Raspberry Pi because I've run that analysis. There's only 51 images during that time, which is fine. You get one image every 16 days. So that's 22 images in a year. Let's say we do a little further. Actually, 51 images is fine. Let's look at what those images look like. If I just print that, it's going to give me the image collection, and it's also going to give me the metadata. So cloud cover and all of the, the usual metadata that you expect from the imagery. Now what is really cool is its capability of adding things to the map. And this is why they like JavaScript, is because the rendering is much more beautiful and much more quicker in JavaScript than using IPython leaflets and other things, because you don't have to tile the URLs and stuff like that. So I'm going to add all of this image by first creating a composite. I'm just using a median composite. So I'm taking all the values of all the images that intersects with this geometry and taking the median value of the entire stack, and that is what I'm going to add to this page. Okay? And let's just do this. And that's pretty much it. And the image got added, and it looks horrible, right? So I'm going to take the bands that I'm interested in. I'm stretching the image, so I'm setting the min-max, whatever you need. And then I click on apply. And you have the entire image. So that's why this is a powerful experience, is because if you look at the actual size of the image, or if you look at the actual time it would take for you to download those images, go fetch them, filter with the metadata, and do all of this, it would take a long period of time. For us to do this right now, it took a very short amount of time. The other thing I'm going to show you is something similar to what Sara did, is we are going to, first of all, I'm going to save this visualization because I don't want to keep on going there and typing the visualization. So I'm going to clip this to the geometry. Okay? And then I'm going to add the visualization that I just said. And then I'm going to give it a name. So I'm going to give L8 clip. Okay, and run the same thing again. And what that should do is it has clipped the image now to the boundary. That was fast, right? Okay. Similarly, if I wanted to do something like print filter.median, again creating a median composite. At this stage, the reason I'm creating a median composite is because it's a collection. It doesn't really know how to stack the collection inherently, right? So I have to give it some logic. How do you stack the collection? How do you make it like one pixel as a representative of the entire stack of pixels? Stop me if you have questions. Feel free to just stop me at any point. And I'm going to do band names. And what this is going to do is give me the band names. Again, easy. This is the JavaScript version of it. The reason a lot of people use this is because of the fact that the visualization is pretty powerful, and you can change certain things in it. So I can go ahead and apply a different kind of stretch. But it also comes with certain libraries. So it has an entire set of libraries. I think the last count was 1,000 something plus like things you can do with the collection. So if I wanted to do, for example, an NDVI, right? So I'll just say image normalized difference, and then I'll give it, so that's NIR minus R, so, okay. Yeah, is that correct? Yeah, I think so. We'll find out. And this is calculating the NDVI over the entire collection. And again, I'm going to clip this to the geometry. Run this, and here you can see that this is the values. So areas with high vegetation, you can go in, you can inspect an area where you would expect the vegetation to be positive. NDVI is a measure of greenness that is reflected off of surfaces of vegetations. That's what you measure in terms of NDVI reflectance. There are other indices that do something similar. You have like enhanced vegetation index and soil reflectance, correct vegetation index, and things like that. But we did all of this. If I remove all the spaces in probably 6 lines of code, that's why this is powerful. And the pitch starts from here, is that Earth Engine allows users to do this with publicly available data sets that they already have in their catalog, but they also allow you to bring in your own data sets. So you all get, when you're starting your accounts, you all get 250 gigabytes of storage from Earth Engine. This is not linked to your Gmail quota in any way. Do not be afraid that you're going to fill up your Gmail or Google Drive and it's going to run out of quota. It is not linked to that at all. And once you're nearing, like the end of your allocated quota, feel free to ask them for more. They're generally very nice about giving you more quota. My entire research thesis exists on Earth Engine. And it's, I think, a couple of terabytes, I think 5 terabytes of data sets that are in here, which are planet data sets. And all of these data sets belong to you. What it basically means is Google does not in any way tell you that the data sets are their property because you're storing it with them. The other thing that is important, and I'm going to show you a couple of things, is, sorry, I'm going to show you this part because I realize, yeah, that part is, yeah. Google has a very nice series of like hands-on on how to do this, how to do the analysis, the image overview and visualization characteristics, how you can run each of these analyses. So if you want to do a spectral transformation, if you want to do an edge detection or morphological operations, you can do Canny's edge detection in here. You can do spectral unmixing, constrained spectral unmixing. You can do, sky's the limit. You can do a bunch of cool things in terms of what you can achieve. And I'm going to show you, my friend had made these apps, but I'm going to show you one of them, which was pretty cool, I felt, was this one. You can also build apps, and you don't have to release the source code. You can keep the source code. I mean, technically, the source code is in the back. Someone can actually just look at it. But the idea is you're generally doing things for the betterment of the society anyways, and you want to release that for other people. So this is kind of like NO2 concentration, and this allows you to zoom into any part of the world. And it's rendering, it's on the fly, by the way. So none of these analysis, a lot of these apps don't save these tiles or are not usually using a part of the storage or buckets in Google and saving the analysis in any way. So that's the other thing. Now, one thing you will notice from their page here is their entire tutorial series is JavaScript, right? And that's got me thinking. I was like, that's interesting, but not very useful for someone who doesn't want to work in the JavaScript environment. And I don't expect people to go learn that. So basically, they have a Python API. There's, I think, one link that goes to Python installation, how to do that on your own, on your computer or Docker or something like that. So what we're going to do today is look at the Python API. All of the algorithms that are available in your JavaScript environment are also available in the Python environment. The only problem is there is no documentation for this. And it's horrible, right? So last night, I launched my own website, which is replicating Google's own idea. No way trying to, again, use Google's property in any ways. All I'm trying to do is take their notes and just convert the code. I'm put my aim here, by the way, and I'm asking you guys to send in requests. If someone out here knows both JavaScript and Python, knows how to convert both of them, feel free to do that. But if you look here, the codes are all Python now. They are no longer JavaScript. So yeah, this is just a project that I started a couple of weeks ago. And this is still work in progress. There's a lot of tutorials to convert. But the idea is to give you hands-on on some of those analytics capability that you can do on your backend using just the Python API. If you're not interested in looking at the visualization, you might just be interested in the analytic product. So for example, if you're analyzing 20,000 images or stacks of like hundreds and thousands of images, maybe you don't care about the way it looks. Maybe all you care about is take all of that, put it into a CSV table, and export it out so that I can read it into something else, right? And that you can do using Python. It's not great for rendering the images. It's not great for doing heavyweight lifting when it comes to doing the cool JavaScript kind of environment setups. But you can still do all of the analysis that you wanted to do. And I will share this website for everyone on the page as well. And I'm hoping to share this with Google at some point. I don't know if they'll be happy or not. Oh, you already said you shared this. Thank you for sharing, whoever shared it. OK, so the setup should be done, hopefully. If not, let me know. The next thing I want to do is authenticate the Earth Engine client. So what we installed was a single Python library from Earth Engine. It's called Earth Engine API. And we want to authenticate that. So if I do Shift Enter, it should ask me, did it actually close my notebook? Yeah. Does anyone know if there's like a timeout feature that we can say don't switch it off if you're running this for... Oh, okay. So I've been talking for long. Okay. You can do this, which will authenticate Earth Engine, and it'll generate a link for you. Click on that link and choose the Gmail address of interest to you where you have registered for an account. People who have two-factor authentication will get a notification on their phone at this point. Someone is trying to access your account. It's Google. Don't be afraid. Google is trying to access your account because it wants access to some of the details that you have in your account. It's not doing anything creepy, crawly. Trust me on that. But read the terms of services anyways. You know, it's only something, I think this one is actually shorter. It's not 200 pages long. It's like 14 or 15 pages. It's not too bad. And they'll give you a code. You copy that code, and you go back, and here it says place auth code here. So just paste it right here, and then run this cell, and it'll say successfully saved authorization token. If it hits you with an error, that means you copied it wrong, or something happened somewhere and we need to check. Everyone okay, or have reached this step? Anyone had issues till now? Okay. Oh, one more thing that I wanted to point out, I've actually included this information here, is this part I copied from the terms and conditions page because I didn't want you to read the whole thing. This is where it says that as between the parties, customer own all intellectual property rights in customer data, customer code, and application, and Google owns intellectual property rights in terms of services and software. That means all data, all code that you create on this platform is yours. It's not owned by Google. So, you know, if that gives you a little more ease of mind to work with this platform. Yeah. Okay, so this is the only purpose of this notebook was to actually set this up. I'm going to go and shut this down. And now I'm going to move on to the next notebook, which was satellite images. Now I'm going to do a lot of the things that I showed you in the JavaScript environment. It's going to take a few more number of lines here, but that's only because I have additional functions to actually render the image and do some other stuff. There's a long list of libraries, but they should run just fine. And I'm going to... Is this better? Okay. All this function is doing is converting bytes to a human readable form, not really doing it much. The image collections are actual objects. They're stored as tiles. So Google takes all of these geotiff images, think of them as breaking them into PNG files, and then storing at the different zoom levels. That's exactly how Google Earth works. That's exactly how Google Map works, is that when you zoom in at different levels, it requests different sets of tiles, different sets of images, and that's what's rendered on your screen. So that's exactly what it did, but it's still storing them somewhere, and that storage or that allocation is heavy. So what I'm doing right now is I'm looking at two data sets. One of them is a public data set, which is Landsat 8, and I'm filtering that for a very narrow period of time. This is global because I did not set a geometry. I haven't filtered this with a geometry. So this is global. It's looking globally at every Landsat image that is available for this time period. And it's looking at cloud cover that is less than 2%. I wanted to look at clean images. And the other one that I'm looking at is image collection that I have ingested for you guys, which is a PlanetScope data set, which is for all of 2018 over California, over a narrow part of California. Similar part to what Sara showed you. That's about 1,800 something images. It has complete metadata and images. It's 4-man imagery. It's 3-meter resolution. So it's yours to play with it as long as you want. Okay, if you run this cell, it'll do a couple of things. Let's see. So yeah, it's looking for the number of images. So it's saying that it has 10,533 images that match this time frame, this cloud cover. And for PlanetScope, it has 767 images that matches the same time frame. But the total number of images, if I want just the total number, I will just remove the filter date, or I'll just do this, and I will rerun this. So that's 1,875 images that's available in the Earth Engine catalog. Okay, and you'll also see the size. That's 5.6 terabytes for Landsat, and that's 293.43 gigabytes for PlanetScope. Now remember that Landsat is looking globally all over the world. PlanetScope is for a narrow portion in just US, and that to just California. There's a reason why it's much smaller footprint. Okay. The next thing I want to do is get certain things, like I want to get the metadata from images. So same thing that we did in our earlier notebooks. And we are getting things like the CRS info, and we are getting the min-max, we are getting pixel types. And I'm using pprint or prettyprint to actually do this, to make it a little more approachable. And it gives you dimensions that you might be interested in, like height by width and stuff like that. And now it's printing a specific metadata for a PlanetScope imagery. So this is PlanetScope surface reflectance data. So so I also uploaded the surface reflectance imagery, so you don't have to do that conversion between radiance to reflectance and then to surface reflectance and all that. This is all surface reflectance imagery for PlanetScope. Yeah, go ahead.
Did you want to explain surface reflectance a bit more?
How many of you know what surface reflectance is? Okay, I'm going to explain what surface reflectance is. Going back. Surface reflectance is basically the corrections that is applied to a top of atmosphere reflectance data based on the fact that there is a column of atmosphere that is between the image and the satellite. And that causes a lot of aberrations, a lot of effects on the actual imagery. So those are corrected for using a sensor from MODIS. And there are other sensors that we might be using, but now I think we only use MODIS for those corrections. And it gives you a better representation of what the reflectance is under those atmospheric effects. So it's also often called bottom of atmosphere. BOA is the same as saying surface reflectance data. So that's what surface reflectance is. There's an entire white paper on how we generate that. And Sarah, can you share that on the Slack? Okay, perfect. So this metadata is actually telling you kind of like what algorithm we used and kind of like number of rows, what orbit we were in. So that is low Earth orbit and LEO. Okay, so we printed this, and we also printed the bands. So which is band 1, band 2, band 3, band 4. But in this case, it's blue, green. Is it blue, red, green? Sarah, what was the... BGRN. So blue, green, red, near infrared. So yeah, you don't have to remember this. That's usually in the metadata. I just forgot to include that part. The next function is the interesting function. This is what makes or provides the capability of rendering directly from Earth Engine. Now, Earth Engine has this function where every time you do an analysis, it automatically tiles the results as well. Not only the imagery, but also the results. So every time I did a median composite, it automatically tiled the results, and I can pull those tiles back and render it. So this function kind of just does the tiling thing. And now what I'm going to do is I'm going to add the PlanetScope image on one side of the panel, and I'm going to add Landsat image on the other side of the panel. And this is in no way for me to like bash on one image versus the other. This is just to give you a comparison between the two images. You'll see that PlanetScope will take a little amount of time because it's a heavier image, 3-meter resolution compared to 30-meter resolution. But this is a dynamic imagery. So it's you can zoom into it, and they are linked. So you can zoom into it and give it some time, because sometimes that level of zoom requires time to render. So if you zoom in too far, it requires a little bit of time to render. So you see that it's cleaning up a little bit at the edge. It's taking time. Okay. But you can do this and see the difference in resolution. Again, this is in no way for me to show you that this one is good versus one is bad. It's just to give you an idea of the fact that these both have representations and they both have space in depending on the type of analysis that you want to do. If you're interested in an analysis that works really well with 30-meter resolution, good, go for that, go for Landsat. If you're interested in an analysis that goes with 3-meter data, go for that. There's also variations in temporal frequency, like you already heard, that a Landsat has, I think, 16-day time period. Of course, if you have 2 Landsats in the atmosphere, that comes down to what, 8 days, I think, right? Yeah. That's exactly what's happening with Sentinel-2 dataset, which is the European version of Landsat. I love saying that. It pisses people off, but I was like, I don't care. But it's, yeah, European version of Landsat because it's also free data. They do say that they're also globally consistent, which means they're also globally imaging. But you will see deep down buried in their service terms and agreements, it's that Europe gets higher priority. So you will get more images over Europe than the rest of the world. Landsat doesn't do that. Landsat treats everyone equally. So if anyone is here from ESA or like Sentinel-2, I apologize. This is just, okay. So then we move into the spectral index methodology. Like, how exactly do you calculate about spectral index? Why do you even care about a spectral index? At this point, does anyone have any questions about what I just did till this point? Yes.
Do you know, like, okay, so when it goes to say a lower resolution tile because you're zoomed out,
Mhm.
do they say like what that algorithm is? Like, how do they decide to go from that higher resolution image to lower resolution?
You mean when I'm zooming in?
So if you're zoomed in all the way, you might see the original image.
Yes,
Right? And
yeah.
then as you zoom out, it's giving effectively it's a lower resolution image you're seeing.
Yeah, yeah.
So do they talk about like how they do that tiling at the different levels?
No, the tiling algorithm isn't exposed. That's a good question. It's not exposed, but you can actually print out what level you're looking at. If you just click on an image, which I did at this point, you'll see that it'll give you the zoom level, and it'll give you a scale. So approximate meters per pixel, it'll give you a scale. So if I zoom in further and re-click on this image, and by the way, you can do this in Python also. I just haven't written the code for it, so I'm doing this in the JavaScript environment. But if I'm loading this and going zooming in further, and if I click on the images again, it'll tell me that I'm zooming in at level 11, and the scale approximately is 76.43 meters. So there are ways in which you can figure out what level you're zoomed in while you're looking at the images. But no, the tiling algorithm, what they use to create these different zoom levels are not exposed. I can tell you for a fact that the highest zoom level that they have in terms of rendering is level 18, which is the near value GSD. Like, that is the original resolution of the image. And you can go up to 18 levels above that. Yeah. You don't usually need to, but you can. Any other questions?
Do those levels adhere to any convention or?
Actually, there is. There is an entire theory of image tiling and how the whole world can be represented by 4 large tiles. And as you go further, it keeps on dividing that box, the fourth, the quartile. It'll divide into 4 more and zoom in. So I think every box is like dividing that element of the quartile and going further down. Yeah, but yeah, if you look for like map tiling, there is papers on this. There is different systems or subsystems have their own ways of setting up. Like, for example, Uber uses something known as the hexagonal tiling. So it uses hexes. So if you're actually, interestingly enough, if you're at a certain neighborhood, and if you think that I'm going to walk one straight down and I'm going to get a cheaper price, that may not work because you're still within the same hexagon. Of course, that hexagon is not visible to you, so you can't really walk into a different hexagon. But that's what they use for their tiling system. Okay, so the next thing I want to do is I want to work a little bit more with the PlanetScope imagery. And again, you can do this completely with the Landsat imagery, but since I've given you guys the free PlanetScope data bucket, I want you to show some NDVI stuff. NDVI is one of the many hundreds of indices that you can find. If you'll just look for image indices, there's in fact a website called Index Database. I think it's Satellite Image Index Database, or there you go. Okay, so here, this is one of my favorite websites. You can go here, and you can choose the type of sensor that you're looking at. And it'll tell you the type of indices that you can calculate, what are the purposes, date of launch, comments, some papers. It'll also give you references to papers that they're using to calculate these indices. I think you can go here, show sensors for selected sensor. Okay, so bands for selected. You can also choose sensors, and I can go to Landsat TM, let's do actually Landsat 8, let's do display bands. It'll tell me the bands. And you can look at all the indices. So in our case, what we are doing is we are looking at a very specific index for selected index. And here I'm looking for NDVI. This is probably not the best way of looking for that index. I'm just going to go back and go to the entire list of indices. It's a long list. Okay. Normalized. There you go. Okay. So there's a lot of variations of this index, but what this index is essentially doing is they found out that chlorophyll actually does really good for specific bands, and it has a very specific reflectance characteristic when it reflects off green objects. And when I say green objects, I don't mean things that have been colored green. So it's not like a building that has a green color on top will have the same characteristics, but specifically things that have chlorophyll, that are vegetation in some format or are like active in some way, will have this reflectance. Not only is this true for plants and trees, but it's also true for algae that grow on ponds. So you can find out about scums that are on lakes that are happening as a result of hypoxia, for example. That's an interesting application that people use to look at water quality as a result of function of these characteristics. So NDVI is one of the many indices, but it's just to prove the point that you can do some cool analysis with this. For this one, I think, I wrote the formula wrong here because I initially thought I was going to do this with Landsat 8, but this is going to be band 4 minus band 3. I will correct this in the Jupyter notebook, and I will re-push it, so don't worry about it. This formula is correct. NIR minus red band, which is near-infrared band, minus red band, divided by near-infrared band plus red band. The value of this, because it's normalized, is between -1 and +1, okay? Higher being that the higher it is, the more vegetation there is in a specific pixel. So the thing I'm doing is I'm creating a median composite again, and I am going in and I'm selecting the bands that are red and near infrared, and I'm renaming them to red and infrared, which is good because then I can say that we use the correct formula. Okay, so I'm going to run this. And again, we are tiling these two things. So I'm going to tile the actual imagery, and I'm also going to tile the NDVI imagery. We wait for some time. On the right-hand side is the NDVI. And you can choose a palette that is pleasing to you. I just chose this because I thought it was nice. And you'll see the darker green are areas that have more vegetation. And you can zoom in and see that this is some sort of park or a golf course or something that has vegetation in it. I'm not really sure. I should totally quiz Sara, but Sara doesn't live there either, so. Both of us don't actually live in San Francisco, so we have no idea where we're zooming in. We work remotely. It might be a golf course, it might be, yeah, but what I'm going to do is you can, and while it's rendering, any questions on what I did? The formula was exactly the same as how I did that in the JavaScript environment. I just did, here I wrote it out. I actually did not use the normalized difference function. I did the actual math. I did, NIR minus the red divided by NIR plus red, and then I renamed the band as NDVI. But you can also go in and do NDVI equals to mg dot normalized difference and give band 4 comma band 3, and if I run this instead and run this again, oh, did I do something wrong? No band name NDVI, available bands ND, okay. Oh, I see, okay, yeah. Thank you guys. I'm so glad you guys are catching up. Probably know more about this at this point. There you go. it will give you the same function. The reason I did this is because I wanted to show you that that one line that works on the JavaScript environment also works exactly the same. The only thing you have to be careful about is JavaScript allows true with a small t and false with a small f. Python does not. So yeah, be careful about that. That's the one thing that I've seen to be like pesky, and I was like, oh, that makes sense now. And no curly braces or colons becomes equal sign. That's the whole point of writing that Python docs page. So I welcome all the tutorials that you can send my way. Okay, so here what I'm going to show you is I'm going to try to zoom in again, and hopefully it renders. And the areas with more vegetation, so you'll see the ones with brighter red, areas with more vegetation are all highlighted with more green, and the other areas are not. In the JavaScript environment, you have an inspector tool. You can build something similar in Python as well. I've seen a demo of that. I just did not have the time to build something of that nature. But in theory, because it's loading the tiles and the tiles are aware of that information that's on each pixel. So think of this as large arrays, right? If you click on a certain area, as long as the value exists, it'll return the value of the array. It's not very hard. Okay, so this is what we did. We learned how to query an image collection from the Earth Engine API, get the count and the size of a collection. Then we added a public data set and a private data set, which kind of is public now for you guys, is the planet data set. And then we generated an index from that. Now, while this loads, does anyone have any questions in terms of what we did or anything else you might want to explore with this algorithm or this setup? How many of you have interesting ideas about like maybe something in your domain that doesn't yet require satellite imagery but might be interesting to look at some satellite data? No one. Okay, go ahead. Delineating shorelines, yes. There are actually scripts for that exact thing. I worked with shorelines for part of my work. Let's talk. Anyone else with some interesting ideas? How many of you? Sorry, go ahead.
Well, I know it's been done for urban development.
Yeah, yeah. Like monitoring urban growth over a period of time. Yeah. While this renders, again, Earth Engine time lapse. Since we're talking about urban development, I thought, oh, this would be interesting for us to look at this. This has been created by Google, and it's different places in the world as it is changing using Landsat imagery. And you can go into the other one. There's coastal expansion. Yeah, you can do this whole day, right? It's very calming. Put some music on, like have this run in the background. Construction, for example, you were interested in urban development, so there's construction, and you can go there. I think my favorite is go to Vegas and just look at how 30 years of Vegas has changed from nothing to something. You can see some interesting things happening. Deforestation, of course, that's an interesting and important problem. I work a lot with people who do forest dynamics and monitoring. In Brazil, that's a big deal.
I've used a really cool software in the solar industry to see proposals.
To see what?
The solar industry was the irradiance data.
Okay.
And then just it was mapping out the size of the roof.
Yeah, yeah. I was talking to someone yesterday who was doing something similar and where we are looking at, you can essentially look at the roof data, but also the angle, azimuth angle and reflectance from that. And you can also calculate by placing a false sun somewhere. Yeah. You can do that. You can actually put a false sun somewhere and irradiate and see how much potential solar energy you can generate from rooftops using satellite images as well. Cool stuff. So yeah, I will let you guys explore this in your own time. This can take forever. Yeah, but here you go. Last one, Las Vegas. The interesting thing is the reservoir that you see right next to it, it's like growing, constricting. It's like, I'm thinking about this. I don't know if I like it. You know, it's shrinking and growing. So that's another interesting application. You can actually use the size of the reservoir to estimate the amount of water that is present in certain conditions. The United Nations uses crop yield data to look at whether or not there's enough food that's going to be available if there are drought conditions that are going to be happening in certain countries, and where do you need to stock food for that conditions. Or if you have areas where there's a lot of drought and water might run out, where do I need for emergency water to be available, and how closely can I get to them? So there's lots of applications, and not just humanitarian. I'm just giving you some humanitarian applications, but there are also applications in commercial sectors. There are people who do insurance monitoring. There are people who do all sorts of interesting applications. But yeah, crop yield can also have commercial applications. Okay, so that was it with the first one. Yeah, this is taking forever, so I'm just going to leave it at this point. But you get the picture. Kind of. You get part of the picture. So I'm going to go into the next notebook, which is stratified sampling. I know it's a boring name, but I'll get to it why. So here my interest is a few things. The idea of sampling is not new. If you have a data set that is large enough, there's a probability that you're not going to look at the entire data set. You'll often choose some portions of it. And there are multiple sampling strategies. There's snowball sampling, there's stratified sampling. There's randomization, but there's no true random. So depends on who the person asking the question is, what kind of question you're trying to solve. So if you're doing a household interview, do you do some sort of random allocations of which houses you want to target? Or do you have a more strategized way of looking at those houses? That can be one approach. Similarly, in satellite images, oftentimes you want to understand, let's say something as basic as what does water look like in a part of the world? And the reason I said what does water look like in a part of the world, it sounds very absurd, but water has different characteristics. It's darker, brighter, muddier, shadier, more turbid, and has different characteristics in different parts of the world. So if I tell you that this is the one spectral signature, or this is the value of red band, green band, blue band, just throw me out because that's not true. In fact, a lot of the classes, most classes on Earth, don't have a standard reflectance that is measured and that is being generated yet. What we do have is handheld spectrometers that have been used. In fact, there is a data set library. I keep forgetting, it's generated by NASA actually. It's about, they have looked at different materials and they have generated the spectral radiances from those materials. But for satellite images at different heights, and different cameras, and different sensor calibrations, you'll get different responses. So that's the reason stratified sampling is useful. So what I wanted to do for this problem was to figure out where is land and where is water. And this is what I'm doing using a stratified sampling approach. I'm going to look at a coastline in Louisiana. And I'll tell you a little more of that story later. I'm going to import the library, do the things we do, looking at sizes. I'm going to tell you a little bit about the history of the two data sets that I'm using. Landsat 8 Landsat is one of the oldest Earth observation systems in existence. I don't know of anything else that even comes close to it. I think it was the 1970s when Landsat program first started generating images. Long time ago, when satellites were launched into space, they would often eject a roll or a canister of tape. That tape would then fall to the Earth. It would be collected, and that tape would be then processed into actual images. This is the story of satellite data. I was lucky enough when I was in San Francisco, the person who was driving me in an Uber was one of those people who worked on the cameras of those satellite images, and he told me the story of how those happened, and that was the most interesting ride I've ever had in an Uber ever. And the story then goes back to like how there were still taped imagery. So even though we had a lot of stations that would downlink these images, right? All of these images would still be stored on tapes. So you still have a facility. I don't remember where. Someone from USGS is here, right? Where exactly is the facility where lots of those tapes are stored, Landsat tapes? There you go. So they have rooms, and I'm not even kidding, like rooms filled with these tapes that have now, most of them have now been transcribed into digital formats. But imagine going through and trying to read those data sets would have been harder for you. So Landsat 8 was, I think, this is the latest iteration of Landsat that we have right now. There are already plans for Landsat 9 and Landsat 10 in the works. I'm not sure of the launch dates, but you can look into it. It has always been 30-meter resolution data, except I think Landsat 4, which was 60-meter. I might be wrong on that. Okay, so I am, again, filtering for a specific time frame. So I'm looking at Landsat data. I'm filtering for a specific time frame. And again, with the same cloud cover. Now, this data set, which is JRC GWS, I'm going to show you what this is. And I'm going to go here because the catalog actually tells me, sorry, not here. So JRC, which is the Joint Research Commission from Europe, they actually produced a very interesting paper, similar to the Hansen paper where they did forest laws, where it happened, where it didn't occur. JRC had a lot of field validation data on where in the world was there water ever in the 30 years of observation, and where there was never water during that observation period. So essentially, they could identify and classify every single pixel and tell you whether it was permanent water, not water, if data wasn't available at that point, or if it was seasonal water. So there are 4 types of values that were available in the single banded data, which was no data, not water, permanent water. Okay? This product came out, I think, and you can read the paper. They have the Nature paper listed right here, 2016. So they have the Nature paper right here. You can go to their app and you can visualize it similar to what we're doing. For our purposes, what I'm going to do is I'm going to take a sneaky way out, and I'm going to say anything that is not water is probably land that hasn't changed. Okay? This is my assumption here. As a scientist, I'm just going to go forward with that assumption. Anything that is number 3 or number 2 is seasonal or permanent water. But for the sake of it, I'm going to take more of the permanent water. And I'm going to show you guys how I've used this. I brought this data set into my notebook. And I've filtered it for a similar time frame. But what I wanted to look at was at least 3 years worth of data set. I didn't want to go with just a single year. I wanted to look at 3 years worth of data set. Then I have a smaller area, a subset. Now, this subset, because certain things are just easier to show here, I'm going to do this. In JavaScript, don't forget var is important. Grid and map dot. So this is the area on what I'm looking at. If anyone is interested where we are, it's Louisiana coast. Again, I'm doing this for selfish reasons. This is where my most of my thesis work was. So I already had data on this, and I've already done this a couple of times. But you can choose any box in the world, anywhere. And you can upload shapefiles, by the way, directly into Earth Engine. Earth Engine now has a feature called table upload. So if you go into new table upload, it'll tell you, see, source files can be SHP, SHX, DBF, PRJ. So all of these are shapefiles that you can bring into Earth Engine and directly upload into Earth Engine. Okay, going back to that analysis. So we brought that data in, and I gridded it, and I kind of like bounded it to that area, to that grid only, because I wanted to analyze only for that area. I didn't want to go further than that. Total number of global water data sets that exist within that time frame, if I run it, is just 1. Turns out the paper was published in 2016. They haven't updated that data set yet. There's only 1 data set, which is 2015, that's available. And then I'm going to print out the metadata for this. Again, it'll just tell you that the system index is 31, doesn't matter. It'll give you a year. Earth Engine does this thing where it converts it into epoch time. But it also has a reference that you can just get it back as a normal time. Like, you can write your own converters for doing that. And it only has 1 band, and that band is called water class. And that band has 4 values, the 4 values that I showed you. No data, it's either not water, seasonal water, or water. 0, 1, 2, 3. Okay. Again, I'm getting my tiling algorithm out. And now I'm going to create a widget that is going to show you the same area that I was interested in and the Landsat image rendering of that same grid that I showed you. Okay, so I've chosen different colors. I've said green, brown, and this is, I think, darker brown. I just didn't know how to write it out, so I put the hex code. I was like, I didn't care. Yeah, and then go with blue. So any place that is blue is permanent water. And this is how fragile this landscape is. We're losing a football field every minute or every hour or something like that. And this is huge because this is one of those few areas in the in US which had the first case of something known as climate refugees. Has anyone heard of that concept? Yeah, this is one of those first areas in US where there was climate refugees, where their entire, basically the land was lost. You can't build your houses on stilts if there is no land to build upon. So going away from that story, but looking at it in the terms of like, how do I look at this area and kind of classify what is water, not water? As you can see, it's really fragmented. And I'll zoom out just a little bit to show you that. By the way, if you keep zooming out, it added the entire Landsat and the entire global water mass. So you can zoom into a different location if you wanted to do this analysis also. So what we're going to do is, these were the water class, the single band water class had no data, not water, seasonal water, and water. So what we're going to do is we are going to tell the computer that anything that is greater than or equal to 3, which is permanent water in this case, give me that as a new object, which is water. Okay? Anything that is equal to 1, which is EQ is just 1, means not water, and I am saying that that is land. And I'll show you how I'm going to use that. These two functions are going to allow you to do stratified sampling. So I had to figure out how to do this yesterday because there isn't, like I said, there isn't docs on this. So you kind of have to trial and error it out. But it's not too bad. You know, it's 30, 40 minutes worth of time, but it's not too bad. What we're selecting here is, to this stratified sampling function, what you supply is what is the image where you want the stratified sampling to be, and what are the number of points that you want to plot. So let me tell you what this is doing. Imagine that I'm selecting all of those pixels that are just land, right? And I'm saying drop 50 points randomly throughout that image. That's what stratified sampling is doing. It's dropping 50 points. I don't have to give it any locations. And every time I run this function, it's going to choose different points. Okay? But all I want to do is collect the spectral signature of what land looks like from 50 different points. There is a possibility of oversampling. Don't put 500,000 points. It might be a small enough grid and it gets saturated and it may not be as useful to you. So 50 points is a good enough number that I used. And I'm not saying that that's the standard, by the way. This is something that I have used. And then similarly for water, I have said, give me all those pixels where you know that there is permanent water, and I want the spectral signature of that. And I want to draw 50 points on the water. So it's going to generate those 50 points and 50 points. These points won't overlap because they're drawn on separate pixels. Is that making sense on how I'm doing stratified sampling or why I'm doing it? Any questions? Okay, good. So once that is done, and you can print the info. I'm not going to print it, but I have mentioned it here. There are 50 points here, so it'll print you lat long and like additional info on that, but I'm not going to print the metadata. It's really long. Okay, now what I'm going to do is I'm going to use a function which is a reduce region. So I'm going to take that point, okay, those 50 points, and I'm going to get the mean value of all the bands that are in there in the Landsat images. So you have band 1 till I think band 12 or something. Though most of the last ones are not really usable, but we're not excluding any bands at this point. But all I'm doing is I'm saying for all of those 50 points that are on land or are on water, give me the mean value of those points. So what is the mean representation of land? in terms of the band values. What is the mean representation of water in terms of the band values? Now, mean is not the only operator you can use. You can use median, you can use max, you can use min. Feel free. There's all these operators that you can use. I just use median. I just use mean, sorry. Yeah. So then what I'm doing is I'm giving it a geometry. So I'm saying I only want this to be run on that geometry where there is those geometries or those points that I did the stratified sampling on. And then I'm telling it the scale. The scale here is the resolution of the imagery. For Landsat, that's 30 meter. So that's what I'm doing. And I'm getting the values back. So I'm going to print this out. And you will see that it'll first print you the band names. And that it'll say land mean for bands. So band 1 is 230.12, B2 is this. This is the mean representation of what the land pixel would look like and a water pixel would look like in terms of the image. Making sense? Okay. Now I'm going to use an index. I said that there are thousands of these, right? And we love using a bunch of these. The most commonly used one is NDWI, Normalized Difference Water Index. But there is another one that was, I think, by a paper by Gao, and it was on MNDWI, Modified Normalized Difference Water Index. And we always like updated versions of things, right? So I was like, okay, let's go with the MNDWI for water detection. And what that allows you to do is it does a similar metric to the NDVI, and here the bluer a pixel, for the lack of a better word, but what it's doing is the reflectance of certain bands over water is very, very different and very distinct. And when you do this band math that I'm doing, that highlights it. The higher the value of that MNDWI, the more probability that that pixel is water. So you will get a range between, again, -1 to +1. And let me just add that image. NDVI. Okay, so that's my bad. No, wait. I don't have an NDVI.
You change the NDVI. Yeah.
Where?
That line. The second line, that second file via URL.
You're getting ndvi.viz.
Oh, yeah. Okay, thank you. Thanks, you guys. Awesome.
Group effort.
Is it loading something? Okay. Perfect. So what I've done is, I cheated a little bit here. I did the same analysis in the JavaScript and I found out what the min-max was. You can totally print out what the min-max is. But I cheated and I went in and I was like, oh, okay, it'll look really nice if I visualize it with this min and then this max. So I looked at it and it was like -0.2 to 0.6. But I can still give it like -1 to +1 and it'll still render, but it'll not look as cool. So if I run that, yeah. Okay. A lot of these areas are also areas which have tidal effects. So depending on the time at which these images were captured, you might actually capture portions of the image where land is underwater for a portion of that imagery. And the next day or next time period when you're taking the image, you're like, oh, the land has reappeared again. These are known as intertidal zones. And there are algorithms, more complex algorithms to do that. Read my thesis. It's like totally a pitch for that. Okay, so the next thing that I wanted to do was, you guys have done zonal statistics in the past, so I'm going to run some zonal statistics on that. And what I'm going to do is, first of all, I want to look at the NDWI image, and I want to look at the zonal stats for NDWI. My bad.
Have we done zonal stats already?
Have you not?
I'm just saying.
No, we're just running it right now. And basically what this is doing is it's taking those stratified sampling points and it's running a zonal statistics over each point. It's giving me a mean value. What this allows you to do, you remember how it returned one value of land and one value of water? Imagine I don't want that. Now what I want is, now that I have calculated the NDWI, I want what is the value of NDWI on those points that I used for the stratified sampling. I want the value of those pixels or those areas where there was like land or water, and I want them as 50 distinct values. okay, from the NDWI. That's what you're doing with zonal statistics. Now I'm doing this for both, and I'm using a function called min-max. What min-max allows you to do is to estimate, hey, for water, for those 50 points, what is the minimum value of NDWI and what is the maximum value of NDWI? And similarly, for land, what is the minimum and the maximum? So I click on run again, and it'll give me the range, okay? So you can see right away that for water, the minimum NDWI, actually, I think I was experimenting yesterday with NDVI, but I changed all of this to NDWI. Don't worry, I will correct this later. Okay. So what is happening is for land, the NDWI values are going to be low, and for water, they're not as low. So what I've done here is I've said, okay, if from the earlier min-max value, if I take the NDWI, if I clip it to just the grid, because I don't want the whole world represented in this, and I say that the value is greater than 0.2, just to be on the safe side, okay? Then, and the reason I'm saying it's greater than 0.2 is because the min value, even though it's showing min-max, the min value here is the max value for land, which is 0.1. This is the maximum value of NDWI that you will expect for land. So anything greater than that should be water. That's what I'm going with. That's establishing threshold. There are way better algorithms to do this. There is Otsu's thresholding so that you don't have to look for or search for a min-max and do your own thresholding. You can do interclass variance methods. You can do probability estimators. You can run a k-means classifier with an Earth engine and do this also. So again, I'm running that, okay? And now I'm going to run the last bit. Unmixed tile URL. Yeah, that is.
You just want to use constrained tile URL.
Yeah. This is what happens when you work on it last minute. When I work on it last minute. So it's totally my bad. So what this has given me right now is a binary image. What it's telling me is if a pixel had an NDWI value that was greater than 0.2, classify that as water. If it is less than 0.2, classify that as land. In essence, you have created a binary image that gives you a representation of land and water. So you can slide over. It's not perfect, but it's not too bad, you know? And again, like I said, there are way better ways of doing this. But this is just one of the methodologies in which you can look in and find those thresholds for your localized area of interest. If it's a grid size that is this small, this is totally okay as a method. As far as methods go, this is totally okay if the grid size is small enough. If you're doing like the entire Louisiana coast, which I had to do, I had to break it up into smaller grids and do it. But I also used Otsu's classifier for doing interclass variance and finding out those thresholds. I didn't want to manually plug in those min-maxes and ranges to look at those. So again, choice of algorithm is completely depends on your decision as a user. And that's pretty much it. So what we did was we filtered and masked a collection. So we masked every area that was either permanent water or not water or land. We used a binary mask to create stratified sampling points. So we created those 50 points each for land and water. We used MNDWI to get percentage water and get min-max value from those sampling points. And then we generated a binary land-water classification using normalized difference water index. Now, there are functions. Now you're going to ask me is like, okay, this all is great, right? But how do you get the results out? Earth Engine actually has functions to get those results out. This is not part of the notebook, but I'm going to show you an example. I think I have that here. Trying to remember where I have it. Yeah. So by the way, there is Otsu. So I was telling you that I'm working on this. This is all going to be actually, so when the paper gets published, a lot of these algorithms are already automatically going to go out. So Otsu's, for example, I've already written code that allows you to do the Otsu's thresholding in Python. So I'm just going to make it available publicly as part of the work. You don't have to wait that long. If you want to, just email me. I'll send it to you. But let's see. Open path, and there should be some standalone tools here. There you go. There are ways in which you can, sorry, I'm going to zoom in a little bit. There are ways in which you can identify areas that you want your imagery in. You can give a filter date. And what I was doing was converting them into a collection and then exporting them out one by one. So the beauty of this is it'll already clip the images to the area of interest. Sorry, I forget all the time. To the area of interest, and then it'll export it. You have a couple of options when it exports it. If you have a university account, most universities that use Gmail Suite have an unlimited Google Drive storage. So use your university accounts so you can dump all of this data in your Google Drive. If you don't have that, dump it into Google Drive. When it gets full, just download it out, clean it, and rerun again. Or just buy, it's like, I think, $12 or $13 for 100 gigabytes of storage on Google. So yeah. You can also export it out as an asset. So a lot of these data sets, maybe you ran the NDVI, right? Now you want to keep those NDVI handy, and you want to share just the results, not the code, not the steps, with a colleague and say, hey, I have the NDVIs already calculated. Why don't you go from here? You can generate them as assets. So in my case, I have generated the unmixing, spectral unmixing, and the Otsu-based median analysis, medioid analysis for all of these areas. And I can just add these, and I'm going to add one of them. Let's see. And I can actually I'm going to add the first image. Let's see. And NDWI. There you go. Similar strategy, well, similar kind of strategy in terms of like, yeah, I wanted to get binarization. So my study was to look at what is the amount of land loss that is occurring over a period of time. And because we had high temporal resolution data from Planet, this was looking at every 2 months of land loss. And I wanted to do inter-sensor comparison. So I did this for Sentinel-2, for Landsat, for PlanetScope. I'm not trying to pitch my thesis or work here, even though it seems that way, I know. But it's interesting because you can do like n number of analyses in this format. They have a very helpful group as well where you can ask questions. And yeah, that's pretty much it that I wanted to tell you or talk to you about cloud native analysis. Questions? Yes?
Quality filtering. So I think I saw that you did like cloud filtering.
Yes.
Would they have things, I guess, like fires, like there's smoke that would cover? I mean, like what kind of quality filtering do they have to get rid of atmosphere you can't see through?
Sure.
Issues?
So Earth Engine by itself does not generate any quality tags. But what it does is it takes the XML or the metadata that comes with any type of sensor. So Landsat comes with a bunch of sensors. And I'm guessing that if there's a lot of cloud, it might be detected as cloud. Sorry, a lot of smoke, it might be detected as cloud cover. But it might be possible that FMask is, or the cloud, the cloud tool that they have might be better at generating that. But Landsat is great because it has a thermal sensor. So you can, in theory, go in and see what just the thermal band looks like over that area. And if there's fire, then it'll be hotter. So
there's no like data cleanup then, I guess?
You can do data cleanups. So every data cleanup that you can do here is based on the image that you're adding. So for example, if I'm adding, so okay, print first. Okay, so I have all of these metadatas can be used for the cleanup that you're talking about. It can only work with the metadata. You can write your own functions that'll do some sort of extra calculations on an image, on a collection, and then you can write that as a function. So there is now the capability within Earth Engine where you can write a function and make it available to the rest of the world. So I have functions, for example, here, which are the modules, where I have ways in which you can create weekly composites, monthly composites, seasonal composites, which are really useful for like agricultural analysis or forest-based analysis. But then I also have this one, which is overlap. So if I wanted to calculate if a certain image collection overlaps my area of interest, give me all of those returns and do something to it, you can do that. You also have top of atmosphere reflectance calculations for PlanetScope, RapidEye, GeoEye, QuickBird, WorldView. So these are functions that you can build on top of it. It doesn't come embedded because these are not the original metadata. They won't process something additional for you. However, if you have a standardized algorithm, right, like the cloud masking, for example, cloud actually, they calculate that at Google's end. They do it at their backend. And then they add it, but they use the same algorithm that is used by NASA or that's used by USGS when they're generating those cloud masks for us. But they don't have any additional metadata fields that they will produce. And that's also to maintain the provenance of the data. If they do too many things to the data, people may not trust it. So yeah, I'm not a spokesperson for Google, so I can't speak for that. But yeah, does that answer your question in some?
Yeah.
Okay.
I can tell you a bit more about that. If you go up to the top and hover over the
Which one?
top of the Landsat 8, hover over that link,
Oh, there's a Landsat 8 link?
or go to in the browser, type the
Oh, I see.
Landsat 8 there. It actually tells you there. And so there's
Yeah, it'll tell you like data provider notes, yeah.
and there's a pixel QA band which has the cloud information. And
Yeah.
you can see it fast.
Yeah, there you go, yeah. And they actually do certain examples that are really nicely done. And in fact, if you go to the examples section, they have cloud masking where you can go into Landsat 8 surface reflectance-based cloud masking, and they have the exact code, and you can run that. And in theory, it'll do cloud masking for you. Not that you could see much of it here because it's compositing after the cloud masking. But yeah, those are some of the things you can do. We also have cloud masking in different sensors available. That is like here, it's only listed as Modest Sentinel-2 Landsat 457, but I already have cloud masking algorithms for PlanetScope and for some other sensors that I've used in my analysis. You had a question.
So can you build operational use cases with the kind of study done where like a month from now you can see how much land was lost?
That's exactly what I did. Yep, that's exactly what I did. I was trying to find a time window in which you will get clean enough images that can be composited together to create images without a lot of holes. Because the problem with cloud masking is it'll just remove them, right? So you'll have nan values or you'll have like donuts or holes in the images. That might be okay in doing some levels of analysis, but if you want to do like pixel to pixel comparison 1:1, it may not be as useful. But yeah, you can operationalize that and write code that does that. In fact, this code that I have, which was for fragmentation analysis, this is what I did, is looking at just that. So here are the things, couple of things, more complicated things I'm doing here. I'm applying OTSU. I'm performing man-Kendall statistics, and I'm getting tau values and z-scores over this area, and I'm doing the differences for each pixel. So first time period minus second time period, then second minus third time period, and so on, and generating that as CSV tables and exporting it out. And if I run this, I don't know if it'll actually run, but the last section of this is the export table to drive. So after doing all of the analysis, like I said, you may not be interested in the picture it's generating because it doesn't look very much, but you might be interested in the fact that it's generating a CSV table and it has two columns. One says system time start, which is the date stamp of when the image was taken, and then it tells you the loss, and then it tells you the gain. And that's all I'm interested in. I may not be interested in what it looks like at all. I'm only interested in the actual value of it. So yeah, you can operationalize it. As far as production level goes or doing any commercial things, right now the way in which Earth Engine is set up is there's a common pool of number of machines that are made available. That number is unknown. No one knows that answer unless someone actually works with them. So if you make a request that has, I want to export 200,000 images, believe me, I tried. You get an email or someone will ask you, is like, hey, are you trying to do something that is like really heavy on the system? And there's a load balancing. Because it's a common pool of resources, the more number of images or more number of tasks that you queue up, it'll slow down your processes further. And that's just to penalize you a little bit to say, hey, slow down, give others a chance as well, because we don't want one person to hog that system. So that's the setup right now. There's no service level agreements with Earth Engine because it's not a commercial product. So you can't say that, oh, I ran the analysis, still going on for 5 hours, give me an answer. Nope, there is no SLAs. There's no contracts with you. There's nothing that says we have to give you this results in this much time. So those are the, the not so good part of Earth Engine. But for people who are researchers, scientists, people who want to just prototype with their data, right? Like you might be a small company who is interested in doing, hey, I have some imagery from various sensors and I want a single platform that allows me to compare this free data as well as commercial data. Where do I do it? This is a good place to do that as a prototype. You don't have to use it for production level analysis, but it's a good place to do at least the prototyping for you. Any other questions? Sarah, what do we do next?
Howdy. I was walking around and I heard a lot of awesome conversations. Basically what Sam and I wanted to do for the last half hour anyway is sort of facilitate awesome conversations because we can't exactly, write a lot of code in the next 30 minutes, but there's a lot of people who have real world use cases relevant to their jobs or their research that they're talking about. So basically we're just going to open this up to kind of formalize this kind of discussion. So a lot of people have had questions for Sam. Seek him out. Also, I've heard a lot of people talking with each other. So if you have a specific, let's say, real-world problem that you're trying to solve, I'm going to open up the mic, actually. If you would like a small group to start talking about this to figure out a way to solve it, come up here and pitch your idea for like 15 seconds. Otherwise, we're just going to keep on having the discussion, and if you need to leave to go to lunch, that's cool. You're not going to miss anything else.
The idea here also, if I just may
Please
add
do,
a little bit,
and I'll repeat it.
If all your idea
So-
will remain yours.
Hang tight just a second for the benefit of the video and everybody in the back who couldn't hear you because we have to use the microphones. No problem. I'm going to repeat what he said. Basically, if you come up with an idea or have a proposal and you'd like to work on this, don't let the conversation end here in this room. Put it in the Slack channel, and the goal is to keep the conversation going. And next year, some of us are going to return or not even waiting till next year, Scipy. We'll try to work out a solution to whatever this problem is. So Sam and I are here especially to help with figuring out what kind of data you might need to solve the problem, the steps that it would take, where to get it, and then also what the steps might be and the process might be to conduct the analysis for this problem. So with that, the microphone is open if you would like to pitch your idea.
If you want to discuss in groups first, maybe it'll take some time.
That's what I'm saying, yeah.
Yeah, come up with some questions that you might want to pitch. If you don't feel like discussing it openly, discuss it in the Slack channel. That's totally fine. You don't have to come up to the
Yep.
mic and talk.
And the very last thing I was going to say, Sam, if you could just give an in-the-microphone pitch for the ENR program, how to sign up.
I'm going to do that.
Thank you.
Okay. So, by the way, what you're seeing on the screen, really cool stuff, is water quality analysis, because there's a gentleman here who is doing some work with algal bloom and water quality, and I was showing him how we were doing some Landsat-based analysis for looking at water quality. Okay, education and research program. If you go to planet.com right now, I'm the one who approves these applications, so you'll be approved as long as you're an education and research eligible user. I have to say that, so that's important. If I go into markets, there's a section that says education and research, and there's a button that says apply now. What that'll do is take you to this Google form. Doesn't look like a Google form, but it is. Fill in your details, including your university email address, your university role. You can be a postdoc, you can be an undergrad, a professor, a research technician in a lab at a university. Doesn't matter. As long as it's a degree-granting university, it's established somewhere in the world. We have some restrictions for some countries, but yeah, we can talk about that later. But yeah, fill in those and submit the questionnaire. And once you do that, that whole list comes to me and generally gets approved within a week or two. That depends because I'm the only one reviewing a list, and we get about 200 users per week. So I have to review those 200 and manually go through and check if you're truly a student or not, or truly a university person or not. So feel free to apply at this page. I'm going to directly put a link to this page here. I think this is my site.
And remind us for the video what the purpose of this program is. What do they get?
Yes. Clearly, my colleague knows more about this, but The education and research program was started, I think, 2015, around 2015. And the idea of the program was to enable people who are working at different universities, different educational labs and research facilities to come ask us questions without the limitation of having zero high-resolution data set. At that point in time, there were very few providers that would give high-resolution data set. And even if they did give it, they would only provide it either during disasters, so there was disaster data that would be available, or they would only provide it using some sort of grant or foundation, but it'll be a one-time thing. Like, for example, I remember DG had a 1,000 square kilometer grant that was high-resolution data. Doesn't exist anymore, by the way. Foundation, DG Foundation doesn't exist anymore. So the idea here is to enable you to do consistent research over different AOIs. What you get as an education research user is your AOI is unlocked, which means you can zoom into any part of the world and you can download 10,000 square kilometers. So 1 month, like in January, you know that there's less clouds over some part of the world. Go zoom into that area and download that image. In February, go to a completely different part of the world and download that other image, or those other collections of images. And there are lots of amazing applications and tools that's in developers.planet.com. Sara works on this, my colleague, and she has created this entire website. It has API docs, it has Planet Schools, so you can learn about how to use a couple of these. It also has those amazing notebooks that she demoed here on like searching for imagery, how do you actually download the imagery, the metadata, and all of those things. Anything I'm missing?
No, you're awesome.
Okay, cool. So any questions on the ENR program? We're going to put our email addresses somewhere, official email addresses, and you'll be able to just email us questions or email me questions about ENR, and I'll try to resolve those.
That's it.
Okay, so the idea right now is just break into those groups. You can form smaller groups or large groups, depending on whatever you want. Come up with a question if you want to frame one, and either put it in the Slack channel or discuss it and email it to us, either or. You're also free to leave if you feel the need to.
Excellent. Thanks, Sam.
Yeah.